the eastern portion of Kerberos Fossae. Visible in this observation is a section of Kerberos Fossae, which are comprised of a series of rifts presently located in Elysium Planitia, just north of the Martian equator. The fossae, Latin plural for ditch or depression, are in close proximity and related to the formation of Athabasca Vallis, which lies to the west. These rifts are collapse features believed to form by volcanic and tectonic processes. In this composite image, we can see that the rift is not continuous, but discontinuous and offset. The offset could be the result of a pre-existing subsurface discontinuity, such as a fault. The close-up view of HiRISE infrared color shows us a plethora of information about Kerberos Fossae and the great amount of detail that HiRISE captures. The clear view of boulders strewn in shadowed areas of the rift is a testament to the high signal-to-noise capability and high resolution of the HiRISE camera. Aeolian dunes, along with boulders deposited from erosion of the rift walls, are also visible in detail. Using the pixel length of the shadow within the rift, the incidence angle of the sun at the time of the image was taken, and some trigonometry, the approximate depth of the various sections of Kerberos Fossae can be estimated. Based on this simple method, an approximate depth is 260 meters. This estimate suggests that the rift is as wide as it is deep. Another remarkable aspect of this image is the stark contrasts it captures. Light-toned dusty surfaces that surround the rift versus the dark blue basaltic sands and the shadows within the rift. The detail that HiRISE can provide is indeed phenomenal. And as demonstrated here, the infrared color provides additional information. Why, for instance, is the floor of Kerberos Fossae a deep blue? And why is there such a contrast with the orange-grayish Martian surface? It's not water. The volcanic and mafic sand contains unoxidized iron, which appears as a deep blue, while the Martian surface is covered by oxidized iron-bearing dust, which appears orange-grayish.
Ariz 3 and the Martian. In the novel The Martian by Andy Weir, stranded astronaut Mark Watney spends most of his time at the Ariz 3 site in southern Acidalia Planitia. The book describes Acidalia as flat and easy to drive over. He even drives to the Pathfinder landing site and back. This region of Mars is actually far more diverse, interesting, and hazardous to drive over than depicted in the novel. These two images are close to the Ariz 3 landing site as shown in a map at the front of the novel, and show many mounds, perhaps ancient volcanoes resulting from lava-water interaction or eruption of muddy sediments. Much of Acidalia Planitia is covered by dense fields of boulders up to several meters high that would be difficult to drive around. There are also fissures associated with giant polygons with steep rocky slopes that would be impassable. There are elongated fields of dense secondary craters where the surface is extremely rough at scales near the size of the rover. When our hero travels into Arabia Terra, it's described as much rockier than Acidalia, but the opposite is generally true. Much of Arabia is dust-mantled and smooth at the scale of a rover. People commonly assume that smooth at large scales, kilometers, means smooth at small scales, meters to tens of meters. Often on Mars, the exact opposite is seen. Large, flat, low areas are more wind-scoured, removing fine materials and leaving rocks and eroded bedrock. For HiRISE, this is Phil Plait from badastronomy.com.
Sand avalanches in Maro Patera. One of the major extended mission objectives for HiRISE has been to re-image parts of the surface to look for changes. Such observations can tell us what processes are active today. This image was acquired as part of a series to look for sand movement in Maro Patera, not far from the active sand dunes of Nili Patera. Our image shows that sand dunes are missing downwind, to the left, of a crater near the center of the observation, because sand falls into the crater and is trapped. Zooming in on the sand-coated crater wall and comparing it with older images revealed a surprise. Several major sand flows slumped down into the crater, towards the upper left, leaving small ridges called levees along their path and rounded piles of sand at the end. What caused these slumps? Dry ice, which is thought to cause flows in some gullies and the North Polar dunes, does not occur this close to the equator. There is no sign of recurring slope lineae, the leading candidates for liquid on the Martian surface. Instead, it is most likely that these were dry flows. They are far larger than the avalanches commonly seen on sand dunes. Dunes in western Medusae Fossae Formation. The dark dunes in the western Medusae Fossae Formation provide some evidence of having a local origin. This image shows no large dunes, but many of the dark sand patches cover slopes up to discrete layers. It is possible that the sand is eroding out from those layers, but slopes can also act as sand traps. A large longitudinal dune. Taken in late southern spring and when Mars is near perihelion, meaning when it's closest to the Sun, this image shows the effects of dry ice sublimation on a longitudinal dune in the far southern hemisphere. The bright patches on the dune are still covered in frost, and the dark regions are frost-free. Longitudinal dunes form when the wind switches between two common directions. Based on the direction of this dune's long crest and the orientation of the smaller ripples, it appears the wind blows from the east and from the northwest. However, it would require taking multiple HiRISE images of this location over time and noticing movement before we could say this definitively. The broad base of this dune may indicate that dune sand has spilled out from areas once covered in ice. During the next Martian southern hemisphere winter, which is about half a Mars year, or 1 Earth year from when this image was taken, this dune will again be covered in frost and possibly solid carbon dioxide ice, unable to blow in the wind until the volatiles begin to sublimate in the spring. Spring in Inca City, Part 4. At certain times in spring, fans take on a gray or blue appearance. This is the time in Inca City when this phenomenon happens. On the ridge at the top of the image, fans have lengthened and now look more gray than the blotches on the arenaeforms. At the bottom of the image, they are distinctly blue in color. Two theories have been suggested. Perhaps fine particles sink into the seasonal layer of ice, so they no longer appear dark. Or maybe the gas that is released from under the ice condenses and falls to the surface as a bright, fresh layer of frost. It is quite likely that both of these theories are correct. Recurring slope lineae in Juventae chasma. Recurring slope lineae, called RSL, are best explained as due to seasonal seeping of water on steep slopes in warm seasons. The HiRISE team has produced digital terrain models, or DTMs, for many key RSL sites, which then allows us to orthorectify the images, correcting the geometry to the view from straight overhead. A series of images over a site are then precisely registered and can be compared to study changes over time. Juventae chasma is a giant box canyon, yet a relatively small segment of the enormous Valles Marineris system. It is breached to the north, leading to the Maha Valles outflow channel. The box canyon may have been nearly filled with water long ago, a couple of billion years, but was released catastrophically when the region north of the box canyon collapsed. That was long ago, and the water in Juventae chasma today, forming the RSL, is a very tiny amount, whose origin remains a mystery. Maybe the water is replenished each year from the atmosphere, or from deeper water or ice. The RSL are active on the north-facing slopes of these hills when the subsolar point is north of this latitude, and they are active on south-facing slopes when the sun is to the south. However, they are not continuously active, and exactly what controls the timing of the activity is not yet known. Seeing beneath the surface in Morava Vallis. Morava Vallis is a small outflow channel in the Margaritifer sinus region of Mars. Several of the interior channels of Morava emanate from a localized region of terrain that is caving in, also called subsidence. This region, comprised of jumbled blocks of flat-topped hills, is known as chaotic terrain. These channels, which emerge from the chaotic region, are separated by elongated hills that coalesce into a single channel before disappearing into the Margaritifer chaos to the north. Chaotic terrains are thought to be the regions where groundwater erupted catastrophically onto the surface, forming highly erosive flows that carved the outflow channels. The hills just downstream of the chaotic source region were shaped into streamlined islands by the erosive flows, forming blunt, rounded ends in the upstream direction and tapering towards the north in the downstream direction. Although windblown sediments now cover the original flood-carved channel floor in a sea of dunes, a 1.5-kilometer diameter impact crater provides a window into the sediment on the channel floor. The crater exposes several layers along its upper walls, including a distinct bouldery layer just below the mantle of windblown sediments. These boulders may have originated from the eruption site and were transported and emplaced on the channel floor by high-energy floods. Alternatively, these bouldery layers may be lava that subsequently flowed across the flood-scarred channel floors. Spring in Inca City, Part 5. A significant event has occurred in Inca City. The layer of seasonal ice has started to develop long cracks. This is visible in the orange-colored band adjacent to the arenaiforms. Fans of dust are emerging from long linear cracks. The cracks form when large plates of ice have no easily ruptured weak spots to release the pressure from gas building up underneath, so the ice simply cracks. There are also more fans on the ridge at the top of the image, and more have appeared in between the arenaiforms. We do not have any analogous processes occurring naturally on Earth. This is truly Martian. Braided tars in Syrtis Major. Transverse aeolian ridges, or tars, are commonly found throughout the Martian tropics, including rocky regions such as Syrtis Major that are largely devoid of dust. These bright wind-blown ripples most often occur in simple sets of ridges with regular size and spacing. Typical tars stand a few meters tall and have a wavelength, that is to say, separation, of 30 to 60 meters. HiRISE has not detected any changes among the tars today, suggesting that they are inactive. In this scene, we see tars with a highly unusual morphology. Instead of single ridges, we see sets of small ridges that are separated by about 50 meters. The smaller ripples are spaced only 5 to 8 meters apart. Between the smaller ripples are even smaller striations that are perpendicular to the ridge crests, with regular spacings of less than 2 meters. This image raises a number of puzzling questions. Why are the ripples organized into two distinct wavelengths? Did the different wavelengths result from different processes or from different conditions? When did these wavelength-specific conditions or processes take place? Did they occur together, or did they alternate? Or did one take place after the other? Were the processes depositional or erosional, or both? The complexity of Martian tars makes us think twice about any single explanation for their origin. Dunes and wind streaks in Arabia Terra. Arabia Terra is one of the more dusty regions on Mars, where ever-falling red dust covers the surface, allowing only minor variations in color and tone. One exception is when wind-driven, dark-toned sand moves across the surface, ejecting the bright dust into the atmosphere to reveal the dust-free surface below. This high-rise image shows sand dunes with surrounding larger, teardrop-shaped light streaks pointing west or to the left. This orientation, along with the morphology of the local dunes, indicates winds from the east have stripped sand particles off the dunes and carried them downwind to form these light streaks. More importantly, active sand has a role in the slow erosion of the rocks here and the overall landscape evolution of the region. Spring in Inca City, Part 3. In Inca City, another week has passed, and there are a few more fans on the ridge. We are studying the sequence of spring activity with the help of citizen scientists at the Planet 4 website. Citizens of planet Earth log on and identify and measure fans and blotches in the south polar region of Mars imaged by HiRISE. With their help, we can study the polar weather by looking at how the fan directions change through the spring. See how the number of fans and blotches depends on the thickness of the ice layer and how high the sun is in the sky. Spring in Inca City, Part 2. It is about 2 weeks later in Inca City, and the season is officially spring. Numerous changes have occurred. Large blotches of dust cover the arenaiforms. Dark spots on the ridge show places where the seasonal polar ice cap has ruptured, releasing gas and fine material from the surface below. At the bottom of the image, fans point in more than one direction from a single source, showing that the wind has changed direction while gas and dust were flowing out. Was the flow continuous, or has the vent opened and closed? Spring in Inca City, Part 1. Every winter, a layer of carbon dioxide ice, or dry ice, condenses in the southern polar region, forming a seasonal polar cap less than 1 meter deep. Early in the spring, the ice layer begins to sublimate, going directly from a solid to a gas, from the top and bottom of the ice layer. Under the ice, gas pressure builds up until a weak spot in the ice layer ruptures. The gas rushes out, and as it escapes, it erodes a bit of the surface. Fine particles are carried by the gas to the top of the ice, and then fall out in fan-shaped deposits. The direction of the fan shows the direction of either the wind or the downslope. If the wind is not blowing, a dark blotch settles around the spot in which the gas escaped. This region is known informally as Inca City, and it has a series of distinctive ridges. On the floor between the ridges are radially organized channels, known colloquially as spiders, more formally called arenaiforms. The channels have been carved in the surface over many years by the escaping pressurized gas. Every spring, they widen just a bit. This was the first image to be acquired after the sun rose on Inca City, marking the end to polar night. A few fans are visible emerging from the arenaiforms. Hardened dunes in Arcadia Planitia. HiRISE, with its high resolution and 6 years in orbit around Mars, has shown that many dunes and ripples on the planet are active. This demonstrates that in some areas, sand is loose enough and wind strong enough that significant change can occur. Nevertheless, other Martian dunes are clearly inactive. This image in Arcadia Planitia shows dunes in a crater. Unlike active dunes on the planet, those here are bright, and zooming in, there are several lines of evidence indicating that the dunes have become indurated, that is to say, hardened, into cohesive sediment or even into sandstone rock. For example, the dune field at the southern edge is cut off by a steep cliff, indicating erosion of hard material. Although fine-scale ripples on the original dune's surface are preserved, we also see large-scale fluting from southwest to northeast, a common texture associated with wind-induced sand abrasion. How these dunes became indurated is unknown. One possibility is that this area of Mars was buried and then exhumed, a process that seems to have occurred many times in the Martian past over various areas of the planet. During burial, compaction and possibly groundwater circulation would have indurated the dunes, leaving them as a hard sandstone that, when exhumed, was subsequently partially eroded. Sand sources near Athabasca Vallis. This image shows a small channel cutting into young volcanic lavas in a region where massive catastrophic flooding took place in the relatively recent past. The Athabasca Vallis region includes a vast lava flow, thought to be the youngest on Mars, with even younger outflow channels that were carved by running water. The source of the water is believed to be the Cerberus Fossae valleys to the north, which may have penetrated to an overpressurized aquifer in the subsurface. Nowadays, erosion by gravity, wind, and frost gradually wears down the rims of outflow channels. In this scene, we see dark materials along the channel rim that were probably exposed by this erosion. The dark materials are less red than the surrounding surface, so they appear blue in this enhanced color picture. Viewed close up, the dark materials show ripples that suggest that they are made up of mobile sand. It's possible that this sand originated elsewhere and simply collected where we see it today. But the fact that sand is not found elsewhere in the scene suggests to us that it is eroding out of the volcanic layers at the retreating rim of the channel. Sand sources are important because mobile sand grains have only a limited lifetime, wearing down and chipping apart each time they impact the surface. Erosion of the volcanic materials in this region may provide sands to replace those that are destroyed. Few such sand sources have so far been identified on Mars. Search for Mars 2 debris field. Despite the recent successes of missions landing on Mars, like the Mars Science Laboratory or Curiosity, or the arrival of new satellites, such as India's MOM orbiter, the Red Planet is also a graveyard of failed missions. The Soviet Mars 2 lander was the first man-made object to touch the surface of the Red Planet when it crash-landed on November 27, 1971. It's believed that the descent stage malfunctioned after the lander entered the atmosphere at too steep an angle. Attempts to contact the probe after the crash were unsuccessful. HiRISE acquired this image to aid in the search for the missing lander. If the Mars 2 debris field is found, it could serve as a future landing location for a mission to study the effects of crash landing on the Martian surface and effects of aging on man-made objects. Which way is up? This image shows an impact crater that was cut by lava in the Elysium Planitia region of Mars. The relatively flat, shallow floor, rough surface texture, and possible cooling cracks seem to indicate that the crater was partially filled with lava. The northern part of the image also shows a more extensive lava flow deposit that surrounds the impact ejecta of the largest impact crater in the image. Which way did the lava flow? It might appear that the lava flowed from the north through the channel into the partially filled crater. However, if you look at the anaglyph with your red and blue 3D glasses, it becomes clear that the partially filled crater sits on top of the large crater's ejecta blanket, making it higher than the lava flow to the north. Since lava does not flow uphill, that means the explanation isn't so simple. We have seen much evidence for lava flows in this region that flowed to much higher levels than the present surface, then deflated or drained away. That may have happened here. Lava flowed from the north to south to fill this crater, but then it drained back to the north, carving this channel. The topographic information that we gain from having a stereo pair let us answer a question that we could not have with only a single image. This is a great example of why we take stereo images, where the two images are used to make a 3D image. A light tone deposit in arsenious chaos. The objective of this observation is to examine a light tone deposit in a region of what is called chaotic terrain at the base of the Valles Marineris Canyon system. The deposit displays a rough surface, in contrast to the smoothness of the surrounding area. Some parts of the surface appear as if they were eroded by a fluid flowing north and south, or perhaps sculpted by the wind. This area is also visible in a context camera image. This deposit may be related to interior layer deposits in the Valles Marineris, where it's been suggested to have formed in an ancient lake. Perennial frost in a crater on the northern plains. Most surface ice on Mars is temporary. The polar layer deposits are thick stacks of permanent water ice at each pole, and the south polar residual cap may be a permanent, although dynamic, layer of carbon dioxide ice. However, at lower latitudes, seasonal frost, mostly CO2 but some water ice, comes and goes each year. Some outliers of water ice are found near the north polar layer deposits. In many cases, these have accumulated significant thickness, as in Louth Crater. In this case, a thin layer of bright frost was visible in a HiRISE image in early summer, covering part of the wall of a crater. However, the thickness was small. There is little visible effect on the topography of the crater. HiRISE monitored this location through the rest of the season and found that the frost remained all summer. So this is a perennial ice patch, although the edges shrank slightly over the summer. Carbon dioxide is not stable under summer conditions, so this is likely a patch of water ice. It may be that it's in the early stages of accumulation, or that the equilibrium amount of ice in a small crater relatively far from the pole is thin. A still unexplained feature of this crater is the diffused dark smudges visible on the crater floor. These resemble defrosting spots, which are visible on carbon dioxide ice in the early spring, but they occur on frost-free areas and survive throughout the summer. Mounds of layered material on the west edge of Melas Chasma. Melas Chasma is the widest segment of the Valles Marineris Canyon and is an area where the Mars Reconnaissance Orbiter has detected the presence of sulfates. This image offers a view of an excellent contact between layered deposits that post-date the formation of Valles Marineris and possible deposits that predate the canyon's formation. The materials are near interior layered deposits that contain sulfates and likely have hydrated minerals. At high resolution, we can have more accurate mapping of the stratigraphic relationships and contacts. Enhanced color can help to differentiate between geologic units and for mapping of sulfates. A collection of landforms in eastern Elysium Planitia. This image shows a great deal of geologic diversity in a rather small area. In the northern section of the image, we see flat terrain that is probably an ancient lava field. This field runs up against a mesa with slopes that show several dark streaks, possibly freshly disturbed material that is darker than the surrounding area and hasn't had time to fade. These dust avalanches are common in dust-covered regions on Mars. Further south, we also see a line of pits and also fretted terrain before we come across a network of channels and depressions that dominate the southern portion of the observation. Dome and Barshan Dunes in Newton Crater. This observation shows a small sand dune field on the floor of Newton Crater, an approximately 300-kilometer-wide crater in the southern hemisphere of Mars. The image shows both dome and Barshan dunes. Both these types of dunes are also found on Earth. Barshan dunes in particular are common on Earth and are generally crescent-shaped with a steep slip face bordered by horns oriented in the downwind direction. Barshan dunes form by unidirectional winds that are good indicators of the dominant wind direction. In this case, the horns of the Barshan dunes are not very distinct, but appear to indicate that the strongest winds blew approximately southeast to northwest. Note the pattern the dunes form around a bright streak in the downwind direction behind a crater in the center of the image. Bright slope streaks in Arabia Terra. This observation shows bright and dark slope streaks in craters in the Arabia Terra region. Slope streak formation is among the few known processes currently active on Mars. The cause of slope streaks is still debated, but both dry and wet processes have been proposed to explain their formation. They are mostly commonly believed to be formed by gravity-driven movement of extremely dry sand or very fine-grained dust in an almost fluid-like manner, analogous to a terrestrial snow avalanche, exposing darker underlying material. The darkest slope streaks are the youngest and can be seen to cross-cut and lie on top of the older and lighter-toned streaks. The lighter-toned streaks are believed to be dark streaks that are brightening with time, as new dust is deposited on their surface. Smaller craters on either side of the larger crater in the center of the image. Continual dune and ripple migration in Neely Patera. Neely Patera is a region on Mars in which dunes and ripples are moving rapidly. Of the dunes exhibit new avalanches. These results show that Neely Patera and other regions on Mars are areas of active sand migration and landscape erosion. Banded tars in Iapygia. The tropics of Mars are commonly littered with small bright ripples that were somehow shaped by the wind. Called transverse aeolian ridges, or tars, The features stand up to 6 meters tall and are spaced a few tens of meters apart. They are typically oriented transverse to modern-day wind directions and often found in channels and crater interiors. The physical process that produces these features is still mysterious. Most TARs display no evidence of internal structure, so it is difficult to discern exactly how they were formed. While validating a HiRISE digital terrain model of the area, Sarah Madsen of the University of Arizona discovered these rare banded TARs in Iapegia, south of Syrtis Major. These features resemble TARs elsewhere on Mars, except that they show bands or layers on their northwest faces, but fewer or none on the southeast sides. One possible interpretation of this strange layering is that these particular TARs are made up of wedge-shaped layers, as shown in a schematic cross-section illustrating the inferred structure of the TARs. If this hypothesis is correct, it implies that the ripples grew vertically over time, as material accreted at the crests of the ridges. It also suggests that the banded slopes faced upwind. This observation might provide a valuable clue to the formation of TARs elsewhere on Mars if they have a similar internal structure. But that structure cannot be seen because they are made up of homogeneous materials that are uniform in color. Overlapping lobate lava flows in Daedalus Planum. Lava flows south of Arsia Mons in Daedalus Planum transition from younger flows with elongated, sinuous morphologies to the northeast to older, broader lobes and sheet flows to the southwest. The timescale we're talking about is approximately 100 million to 1 billion years. At the southern margin of the Tharsis region, older, probably 3 billion-year-old volcanic plains have been identified where Tharsis flows contact the ancient highlands. The high resolution of HiRISE images allows for reconstruction of complex volcanic surfaces, including delineation of individual flow lobes and superposition relationships within a flow field. This image shows a contact between two of the younger, elongated flows to the northeast. Populations of small, superposed impact craters can be used to derive relative and absolute age constraints for these individual flows and flow sequences. A possible landing site in Arum Dorsum for the ExoMars rover. One of the important roles of HiRISE is to take high-resolution images of potential landing sites for future landing missions. This image is of an area called Arum Dorsum, also known by its old name, Oxia Palus, that has been suggested for the 2018-2020 ExoMars rover because it contains an ancient, exhumed alluvial system. Imaging is needed both to check for boulder fields and other obstacles, as well as checking the scientific justification for choosing a site. This image is one part of what we call a stereo observation, where taking a view at a different angle from another orbit of the same areas will allow a 3D model, a digital terrain model, to be prepared. With this model, accurate measurements of slopes can then be made. Although it won't show the exhumed alluvial system, images of the area are needed to characterize the landing site. The main image of the Arum Dorsum site contains a relatively fresh 150-meter diameter impact crater with associated boulders. This small 1-kilometer square part also shows signs of erosion into an overlying plateau, plus recent formation of some transverse aeolian ridges called TARs within the resulting valley. Overall, however, the site has relatively few obstacles for a lander. Chaos in Eridania Basin. Eridania is the name of a topographically enclosed basin located in the southern highlands of Mars that has been suggested to be the site of a large ancient lake or inland sea. A chaotic jumble of relatively bright blocks sits on the lowest floor regions of the basin, sampled in this image. These blocks contain a variety of hydrated minerals that could have formed in the water, perhaps preserving information about an ancient habitable environment. This lake or sea partially drained to form the Mahadim Vallis, a large channel that itself drained into Gusev crater to the north. The Spirit rover landed in Gusev crater in 2004 to study the expected lake deposits, but found that the floor of the crater had been covered by lava that was younger than the fluvial activity. Eridania is a better place to find lake sediments, but is too rough and dangerous for the landing systems sent to Mars in the past. Mantled terrain in the southern mid-latitudes. The mid-latitudes of Mars, approximately 30 to 60 degrees north and south, are covered in ice-rich mantling deposits in varying states of degradation. This mantle is thought to be deposited as snow during periods when the angle of the tilt of Mars' rotational axis, called obliquity, is much higher, which last happened around 10 million years ago. This HiRISE image shows terrain typical of these mantling deposits in the southern hemisphere, east of Raoul Vallis. The pitted texture suggests that ice is sublimating out from the deposits as the region is warmed under current lower obliquity conditions. Weird crater. This feature has a strange appearance, as if the crater has feet with toes sticking out of two sides. Let's try to explain this. First, there was a highly oblique impact event with the bolide, or meteorite, striking the ground while flying almost horizontally over the surface. Such oblique impacts tend to send ejecta in two directions to the sides of the bolide trajectory, rather than in all directions around the crater. However, there was ice near the surface, covered and protected by the ejecta, and the unprotected ice sublimated at some later time, so the ejecta now appears especially thick. Also, there were layers of dust, maybe along with ice, deposited inside the crater. Or maybe something else happened, but likely involving the ice that comes and goes in the middle latitude regions of Mars. A new impact crater near NASA's InSight landing region. InSight is a NASA Discovery Program mission that will place a single geophysical lander on Mars in September 2016 to study its deep interior. InSight needs seismic signals, and one sure way to get them is from the impact of bolides onto Mars. InSight can detect large impacts that are far from the lander and smaller impacts that are closer. This recent HiRISE image, acquired to certify a landing site for the mission, shows a distinctive crater with a very sharp rim and ejecta that is darker and bluer than almost all of this dust-covered region. This must be a very recent impact because there hasn't been sufficient time for atmospheric dust to settle over this spot and re-brighten the surface. In fact, previous images suggest it formed between 2008 and 2012. This illustrates the type of feature that orbiting cameras will search for during the InSight mission to attempt to correlate seismic signals to the point of origin. The side of Chasma Boreale. Chasma Boreale is the 560-kilometer-long valley that cuts through the northern polar layer deposits of Mars. The section that it exposes shows fine-scaled layering and a major unconformity where the azimuth of the beds changes markedly. This is a characteristic of the polar layer deposits. The formation of the unconformity suggests a time when lower sediments were being eroded rather than deposited. The polar layer deposits are weakly cemented rocks, and so lying over the scarps you can see lines of mass wasting, where dust and sand-sized particles have slumped downhill. This image is part of a planned stereo pair and was in the late summer in the northern hemisphere of Mars. Comparing images like this to those taken in previous years and in different seasons allows a more accurate understanding of current surface processes on the red planet. An irregular upright boulder. This image was targeted to cover part of a small chaos terrain where there are lots of steep slopes. A close-up shows a boulder or rock casting a long shadow at the end of a boulder trail down the slope, and we can see it move from upper left to middle right. The trail has an odd repeating pattern, as if the boulder couldn't roll straight due to its shape. The sun angle and shadow length indicate the boulder is about 6 meters high, whereas its width, as seen from overhead, is only about 3.5 meters. So indeed, it has an irregular shape. Furthermore, it came to rest with its long axis pointed up. What gullies can say. Right past the sharp but warped rim of this ancient impact crater are deposits of winter frost, which show up as blue in enhanced color. There are two possible science goals that we can study here. What does the terrain look like during the Martian summer? Because HiRISE resolution can track changes over time. And second, could the gullies in this crater be a reasonable place to look for a recurring slope lineae to occur? The slopes of certain craters have been home to these phenomena in other regions as well. The busy flank of Arsia Mons. This observation shows an incredible diversity of ancient lava tubes and impact craters filled with sediment on the flank of Arsia Mons. The rationale for this observation is to get a better look at those lava tubes, their shapes, morphology, and erosional degradation, which ultimately might help to date the active period when lava flowed through the volcano. We will also be able to see in high resolution an erosional snapshot of the collapsed lava tubes and how they have been modified by dust falling from the air, mass wasting, and impacts over time. Water-bearing rocks in Noctis labyrinthus. The bright rocks in this image have minerals that contain water. These water-bearing minerals are found using the companion instrument on the MRO spacecraft called CRISM. By combining the spectral data from the CRISM instrument with the high-resolution visible images taken by HiRISE, scientists are able to speculate how water deposited and/or altered these rocks. Many of the depressions in Noctis labyrinthus contain water-bearing minerals, suggesting that water was available and persistent in this region during the late Hesperian to Amazonian epochs on Mars, a time when the climate is believed to have been dry and cold like we see today. The icy surface of the North Polar Cap. At Mars' North Pole is a dome of icy layers ranging up to 2 kilometers thick, roughly analogous to the Earth's ice caps in Greenland or Antarctica. Although not visible here, the dome is characterized by incised spiraling troughs that reveal sequences of layers thought to reflect varying climate conditions over the time they were originally deposited. This image is of an area on top of the surface of the polar dome between the troughs, vast, generally smooth, flat plains composed of a thin layer of very pure water ice. This image also shows that this thin ice layer has a rough texture, composed of knobs, ridges, and depressions on the scale of 1 to 10 meters. This texture is only beginning to be studied with the high-resolution capabilities of HiRISE. The details of the texture varies around the polar cap, but the causes of the variation are not yet clear. This image has two particularly interesting features. One is that the surface dips into a depression towards the southwest, where the texture of the ice surface appears to change. The other is that there is a fracture or chain of pits in the southeast, which is a rare feature. The brightness, composition, texture, and small-scale features of this ice layer that covers most of the polar dome are important as they influence the local energy balance, such as the amount of sunlight reflected and absorbed, which in turn influences polar-wide climate and the stability of ice. Ancient lake sediments in a crater. This image shows some interesting fractured materials on the floor of an impact crater in Arabia Terra. There is a channel entering the crater and exiting the crater, as we've seen in a context camera image. This channel, along with an unusual deposit on the lowest part of the floor, suggests that there was once an ancient lake that deposited sediments here. Our enhanced color sample shows layered deposits, some with polygonal patterns, as might be expected from lake sediments. The fracturing of these deposits might have resulted from the sudden breaching of the crater rim, draining the lake. Blockfall on the North Polar Layer Deposits. The North Polar Layer Deposits, or NPLD, are a stack of layers of ice and dust at the North Pole of Mars. The layers are thought to have been deposited over millions of years, as the atmosphere changed in response to the varying tilt of the planet's axis. Learning to read this record could tell us much about the recent conditions on Mars, but we first need to understand the processes that have shaped the NPLD. Comparing this HiRISE image with an observation from the previous Martian year reveals an example of one of these processes: block falls. The slope is steep and fractured here, and a large chunk of dusty ice has tumbled down the slope and broken apart. Scientists on the HiRISE team are studying this process at many locations in order to measure how quickly the NPLD is changing. Other changes are visible on the slope as well. Sand patches have shifted, and in some places on the slope they have been eroded into grooves or troughs, most likely by the carbon dioxide frost that covers the North Pole in the winter. Layers and sand on the floor of Schiaparelli Crater. Schiaparelli Crater is a 460-kilometer-wide multi-ring structure. However, it is a very shallow crater, apparently filled by younger materials such as lava and/or fluvial and aeolian sediments. Most of the floor is covered by a thin layer of dust, but in places where there are patches of dark sand, there is also well-exposed bedrock. This sand-bedrock association is commonly seen on Mars, and most likely, the sand is actively saltating, or hopping in the wind, and kicks off the dust. The enhanced color cutout reveals the relatively bright bedrock, which has a morphology similar to other deposits on Mars, interpreted as dust stone, or ancient dust deposits that have been hardened into coherent bedrock. In summary, one interpretation is that actively moving sand kicks off the loose dust so we can see the hardened dust. A giant cave on a giant volcano. Pavonis Mons is a giant shield volcano, similar to, although larger than, those on the Big Island of Hawaii. These volcanoes are mostly made of stacks of overlapping lava flows. These images and Digital Terrain Model, or DTM, show a collapse feature on Pavonis Mons. The walls of this conical pit are steep, about as steep as it's possible to get before loose material rolls downhill. The material that used to be here has drained downward through the opening seen in the center, into a subterranean void and formed a debris pile. The top of this debris pile can be seen through the opening about 28 meters further down. From this DTM, we can measure how much material drained out of the conical pit, and so estimate how tall the debris pile is. These estimates are enormous. The debris pile itself is at least 62 meters tall. Given that the top of this pile is 28 meters below the rim of the central hole, this tells us that the empty cavity was once 90 meters deep prior to the collapse and infilling. Only a handful of caves on Earth reach or exceed this size, and they all formed by having liquid water dissolve underground limestone, neither of which are readily available on Mars. Sometimes the tops of lava flows freeze on the surface, even while the lava continues to move underground in a lava tube. If these tubes drain, then lava tube caves can be left behind. Sections of the roof may later collapse, creating roof openings, and these openings can be imaged from orbit. Could this be a view into a lava tube? If so, it would dwarf all lava tubes on Earth. It's also possible that this collapse is above some more substantial part of the volcano's internal plumbing system, and collapses deep within the mountain are allowing voids to open up near the surface. It would no doubt be very exciting for future astronauts to explore this mammoth cave and figure out its origin. Global eyes on an impact prize. On March 20, 2014, a dark spot on the surface of Mars, about 8 kilometers in diameter, was noticed for the first time in low-resolution imaging from the Mars Color Imager, or MARSI, camera on board the Mars Reconnaissance Orbiter. Because MARSI sees essentially the whole planet every day, a check of prior images enabled researchers to pin down when the dark spot first occurred. It was absent on March 27, 2012, and then was present the next day. To follow up, the Context camera obtained a high-resolution picture of the area in question in early April. Before and after imaging revealed 2 new large impact craters within the blast zone. At 6 meters per pixel, the Context camera can detect the dark blast locations, but usually cannot directly see the crater that formed the blast. because most fresh impact craters are only a few meters across. This is where the high resolution of HiRISE comes in. Our camera was able to show the fine surface details within the blast zone. The largest of the new craters appears slightly asymmetric in shape and measures 49 by 44 meters in diameter, making it the largest new crater detected on Mars by MRO to date. Both HiRISE and context camera images also show numerous new small landslides within the blast zone. All of these coordinated observations also demonstrate how different teams on the same spacecraft can work together to examine interesting features in greater detail. A revealing landslide in Hebes Chasma. This image shows a prominently stratified transect through the rock of a mountain of material in the middle of Hebes Chasma. The knobby material showing several lineations in the center of the scene may be remnants of landslides that expose these tall, steep slopes in this image and just off seen to the west. Midway up the slope, and to a lesser extent all the way up to the top, a series of alternating lighter and darker bands can be traced running east-west across the ridges and troughs of the outcrop. Just below this, dark material is eroding off of the slope, moving downhill and collecting in fans at the base of the cliff. Exposures of layered rock like these are helpful in determining the types of geologic processes that have occurred at an area over time. And the landslide and fan deposits tell us of how the region is being eroded more recently, including today. An alluvial fan in a low-latitude crater. On Earth, alluvial fans form in desert regions when heavy but sporadic rainfall washes debris from upslope and deposits it in a wedge-shaped fan on the lower slopes below. On Mars, alluvial fans are sometimes visible in impact crater basins, as material from the steep rims is transported radially inward to the relatively flat floor. Because this is a water-driven process on Earth and therefore might work the same way on Mars, scientists study Martian alluvial fans in order to try to better understand the climate history and possible warmer, wetter past of Mars. This image displays an alluvial fan on the floor of a large, 60-kilometer diameter equatorial crater. The ridges are inverted channels, which form when the floor of a channel is more resistant to erosion than the surrounding surface. This can happen if the floor of the channel is cemented by minerals deposited from water, filled by lava, or simply covered by larger rocks, which are hard for the wind to sweep away. Touring a dusty region. Dusty regions on Mars are often considered to look boring in high-rise images because the dust obscures surface features. However, new meteor impacts are found most easily in dust regions, such as the one in this image, because the new impacts blast away the dust at the surface, leaving obvious dark spots that can be seen in images from the Mars Reconnaissance Orbiter context camera. HiRISE will then take a close-up image of the dark spots to image any new craters that have formed as a result of the impact. As well as confirming a new impact, this image also showed other features commonly found in dusty areas: slope streaks and bed forms. A close-up picture of the roughly 2.5-kilometer diameter crater at the bottom of the main image shows ridges on the crater floor where dust has become trapped, and bright and dark streaks down the crater walls where dust has cascaded down the slope. Changing dunes and ripples in Olympia Undae. Olympia Undae is a large field of sand dunes surrounding Mars' north polar ice cap. Because of the high latitude of the dunes, they are covered with water and carbon dioxide frost in the winter and are poorly illuminated. They are best viewed in the summer, when features such as ripples on the dune surface can be seen in detail. In this image, we see the dunes in early summer of this year. The dark material is sand that makes up the dunes. Between the dunes, bright bedrock and some lingering patches of frost that have not yet sublimated are visible. Zooming in, we can see small ripples on the dune's surface, as well as the bright interdune areas. This area has been viewed several times by HiRISE, so we can compare this image to past ones to see if there have been changes. Here, we compare the new view to one from approximately a Mars year ago, about 2 Earth years, but slightly later in the summer. The most obvious difference between the images is simply the illumination, with the better lighting in the 2012 image showing finer details. Despite these differences, changes in the boundaries of sand and ripple positions are obvious. This shows that winds, perhaps assisted by the sublimation of frost that may soon loosen sand, are modifying Olympia Undae year to year. The draw of Mars. Sandy landforms formed by the wind, or aeolian bed forms, are classified by the wavelength, or length, between crests. On Mars, we can observe 4 classes of bed forms in order of increasing wavelengths. Ripples, transverse aeolian ridges known as TARs, dunes, and what are called draw. All of these are visible in this Juvente Chasma image. Ripples are the smallest bed forms, less than 20 meters, and can only be observed in high-resolution images acquired by HiRISE, and are commonly superposed on many surfaces. TARs are slightly larger bed forms, with wavelengths approximately 20 to 70 meters, and are often light in tone relative to their surroundings. Dark-toned dunes with wavelengths from 100 meters to 1 kilometer are a common landform, and many are active today. What geologists call draw is the highest order bed form with largest wavelengths, greater than 1 kilometer, and is relatively uncommon on Mars. Here, this giant draw possesses steep faces, or slip faces, several hundreds of meters tall, and has lower order superposed bed forms, such as ripples and dunes. A bed form this size likely formed over thousands of Mars years, probably longer. A large crater in Meridiani Planum. This crater is located in Meridiani Planum, about 20 kilometers northwest of where the Opportunity rover landed in 2004, and about 42 kilometers northwest of Endeavour crater's rim, where the rover has been busy the past few years. Although it's in the opposite direction from where the rover went, this crater is still an interesting place. With a diameter of 4 kilometers, it's the largest crater in the region other than Endeavour crater at 22 kilometers. It's also a little more than 5 times larger than Victoria crater, clocking in at 0.75 kilometers, which Opportunity spent nearly 2 years investigating from 2006 to 2008. What makes it worth checking out? This crater is much older than Victoria crater. Compare the smooth, rounded rim of this crater to the jagged edge of Victoria's actively eroding rim. In comparison with Victoria, this crater is much more filled in by sediments, and its rim is more planed off by erosion. Despite the difference in age and scale, these 2 craters, and most such craters in Meridiani Planum, have much in common. Both craters have exposed bedrock layers along the rim, a field of bright ripples on the crater floor, and dark sand that has piled up along the north inner rim that extends to the northwest on the plains beyond them. Sunken and pitted ejecta. The objective of this observation was to examine the edge of impact ejecta from a crater to the northwest of this area. The ejecta seems to be lower than the surrounding surface. This is unusual because impact ejecta is laid down on top of existing ground. The ejecta also seems to have pits. Perhaps the hot ejecta fell on frozen ground and melted the underlying ice. Equatorial gullies on Mars. Although gullies are most common in the middle latitudes of Mars, they are also found in equatorial regions. This image shows a 3-kilometer wide impact crater with gullies all along the steep inner slopes. An enhanced color cutout better distinguishes the gully deposits from the surrounding boulder fields. These slopes are very steep, so a fluid, like water, is not required to explain gully formation. A surprise land slump in Melas Chasma. HiRISE has been monitoring the recurring slope lineae, or RSL, over the mid-latitude and equatorial regions of Mars. One of these sites is a crater on the floor of Melas Chasma, and an animation shows how the RSL follow the sun, changing slope aspect with the seasons. In one of our most recent images of this site, there was a surprise. A new dark streak just downslope from the RSL. This new streak is about 18 meters wide, whereas most RSL flows are less than 5 meters wide. Closer inspection shows that the dark streak corresponds to a topographic slump, similar to several others visible on this slope. This is one of the largest topographic changes we've seen in equatorial regions of Mars. We are continuing to monitor this location to see if this streak fades in the same manner as RSL, and to understand its relationship, if any, to the RSL activity. If the RSL are due to seeping water, then saturation of a layer downslope could destabilize the slope and lead to such slumps. We continue to be surprised by new discoveries from the Mars Reconnaissance Orbiter after 8 years in orbit. A big block of red bedrock. This image covers a 26-kilometer-wide impact crater northeast of the Hellas Impact Basin. The crater exposes large blocks of bedrock called megabreccia in both the central uplift and in the walls of the crater. The enhanced color subimage from the wall shows a large, approximately 250-meter-wide reddish block. These blocks could be ejecta from the ancient Hellas impact or other large impacts from billions of years ago. The active dunes of Neely Patera. Neely Patera is one of the most active dune fields on Mars. As such, it is continuously monitored by HiRISE, with a new image acquired about every 6 weeks. By monitoring the sand dune changes, we can determine how winds vary seasonally and year to year. This observation is one of the more recent ones of Neely Patera. Compared to an image acquired in November 2012, changes are obvious. The ripples on the dunes have moved, as well as some of the dune boundaries. New landslides on the central dune's lee face are apparent. Such changes in just 16 months, and finer scale changes have been seen in just a couple of weeks, demonstrate the effectiveness of wind in modifying the Martian landscape. Curiosity ready to drill for gold at the Kimberley. Black gold, that is. Organic material which could be a biomarker, sign of past life, the holy grail of Mars exploration. Last December, at the fall meeting of the American Geophysical Union in San Francisco, MSL project scientist John Grotzinger talked about what the team learned at Yellowknife Bay and why they would stop and drill again at a place named the Kimberley. The mudstones at Yellowknife Bay had been exposed recently to a geologist less than 100 million years ago. They deduced that this was due to erosion of overlying layers by the wind, and that even younger exposure ages should be possible closer to the scarp. This matters because Mars doesn't have a magnetosphere and thick atmosphere like Earth, protecting us from energetic particles from space that break down organic material. Thus, rocks that have been near the surface of Mars for a long time, geologically speaking, are less likely to contain complex organic material. Complex organic material might be the remains of past life, or at least inform us about past habitability. And when we say habitability, we mean the potential to support life, whether or not life ever actually existed there. The rover had left Yellowknife Bay and it wasn't going to turn around, but similar scarps lay ahead on the way to Aeolis Mons. Last December, they had already chosen their next target, the Kimberley, where they recently arrived, in part because it also has what appear to be geologically young scarps. This new HiRISE image shows the rover approaching one of the scarps. Some regions of Mars are not very colorful, but we can be surprised by local features. This image of an impact crater in the South Syrtis Major region was acquired as a ride-along with a CRISM observation, which targeted this location because that instrument's team expected a distinct composition. Our enhanced image reveals colors ranging from red to green to blue. These are infrared shifted colors, so it's different than what we would see with our eyes. This image of the Neely Fossae region to the west of the Great Isidis Basin shows layered bedrock with many impact craters. Neely Fossae is one of the most mineralogically important sites on Mars. Remote observations by the infrared spectrometer aboard MRO suggest the layers in the ancient craters contain clays, carbonates, and iron oxides, perhaps due to hydrothermal alteration of the crust. However, the impact craters have been degraded by many millions of years of erosion, so the original sedimentary, impact ejecta, or lava flows are hard to distinguish. The bright linear features are sand dunes, also known as transverse aeolian dunes, because the wind direction is at 90 degrees to their elongated orientation. This shows that the erosion of Neely Fossae continues to the present day, with sand-sized particles broken off from the local rocks mobilized within the dunes.
Sediments inside Arum crater. Arum chaos is characterized by chaotic terrains overlain by approximately 900 meters of sediments within the 280-kilometer diameter Arum crater. This HiRISE image shows the chaotic terrain as a darker unit with grooves and ridges. The sediments include the brighter rocks that appear very rough due to ridges and furrows. Minerals identified within ARM include sulfates and ferric oxides, which are similar to those seen at the Opportunity rover landing site in Meridiani Planum. It has been proposed that a lake once existed within ARM crater and laid down the sediments.
Bright dunes in Syria Planum. This image shows curious bright deposits in Syria Planum, a high-elevation region near the summit of the Tharsis Rise. Syria Planum has a history of surface changes, documented in telescopic and low-resolution orbital observations since the Viking era. The surface changes result from the relentless deposition and removal of bright dust, as the dust is transported by winds blowing from north to south across the rocky dark surface. Isolated patches where thick dust deposits have accumulated can be identified in Themis nighttime infrared observations. The dust deposits are cooler or darker than the rocky surface both in daytime and at night. Our HiRISE image was centered on one of these cold spots to observe the interaction of the dust deposits with local topography. Examining the image shows that the dust here has accumulated into linear arrays of broken ridges, spaced about 50 meters apart, and extending from tens to hundreds of meters in length. Dust deposits are visible along the rim of the impact crater, but much of the crater's ejected deposits are strangely dust-free. At full resolution, the ridges appear to have a morphology that is clearly distinct from sand dunes and bright transverse aeolian ridges common elsewhere on Mars. Their steep faces are on the upwind side, opposite to the sand dunes. The ridge crests are crenulated, suggesting that the deposits are currently being eroded by the wind. Fine layering is visible in the deposits, possibly indicating an alternation of dust and sand deposition. Deposits such as these hint that while modern Mars is relatively benign, the surface of the planet was battered by much more ferocious winds in the recent past, perhaps during periods of high obliquity. Bright material along the floor of a trough in Noctis labyrinthus. Many of the troughs, or rounded depressions of Noctis labyrinthus, contain bright, sometimes layered materials. This HiRISE image shows an example of the bright material commonly found along the floors of some of the Noctis troughs. Spectral data from the CRISM instrument, also on board the MRO spacecraft, indicate the bright material is hydrated, i.e. contains water. The hydrated material may have formed when water upwelled into the low-lying depression, or when ice within the trough melted due to heating from volcanic activity.
A fissure near Kerberos Fossae with tectonic morphologies. The linearity of the volcanic vent shown in this HiRISE image, in conjunction with evidence of lava flow from the vent, suggests control by combined volcano-tectonic processes. The details of this vent gained by HiRISE should provide insight into those volcano-tectonic processes along Kerberos Fossae fissures in two ways: the nature of both the volcanic products along this fissure, and the geometries of the linear vent, will permit comparison with similar non-volcanic fissures at Kerberos, and results from these comparisons will provide insight into the orientation of the underlying dike system that may have controlled the ascent of water to the surface in the Kerberos region. Future topographic analysis with the second image in order to create a 3D picture will enable us to measure the heights of the associated flows and better understand their volcanic history.
Some of the challenges of exploring Mars are not only finding a safe landing spot for a future rover, but a place that scientifically is compelling as well. HiRISE has taken scores of observations for other missions, like Phoenix and the Mars Science Laboratory, to help those science teams better understand possible terrain hazards. In this observation, we are trying to explore for the presence of minerals called quartz and feldspar, which are even more common on Earth than Mars. Antoniadi crater was identified even prior to the MRO mission as a likely ancient lake, now dry, that was supplied by both surface water and groundwater. Note also how flat the terrain appears, an important factor for any potential landing spot.
A new gully channel in Terra Serenum. Gullies are commonly found in the mid-latitudes on Mars, particularly in the southern highlands. These features typically have a broad upslope alcove, feeding into a channel and debris apron that has been carried from above. HiRISE has discovered many examples of activity in these gullies, likely driven by seasonal carbon dioxide frost. Images to look for such changes have been key targets for HiRISE in recent years, as we seek to understand the full range of surface processes that are active today. This area was targeted to look for changes in gullies that we've previously imaged. Comparing the newer and older images, we see that a substantial new channel formed sometime between November 2010 and May 2013. Material flowing down from the alcove broke out of the old route, eroded a new channel, and formed a deposit on the apron. Observations like this show that gullies are forming today. Although we cannot pin down the season of this event, locations where HiRISE has been able to image more often demonstrate that this sort of event generally occurs in the winter, when liquid water is very unlikely. Despite their resemblance to water-formed ravines on Earth, carbon dioxide may play a key role in the formation of many Martian gullies. Bedding details in layered rock. This beautiful image shows terrific layers and exposed bedrock along a cliff in West Candor Chasma, which is part of the extensive Valles Marineris Canyon system. A context camera image of this area showed that the strata is not entirely horizontal and that there may be crossed beds or lenses pinching out, or some other texture or structure that might give a clue as to the depositional setting of the sediment that makes up these layers. This image shows the area in greater detail and resolution, so we can compare what we have gleaned from context camera and Mars orbiter camera images to develop a better understanding of what we're looking at and how to interpret the past history of the region. Lava flow, front in Elysium Planitia. This image shows details of the lava-covered plains near the equator of Mars. The darker-looking area has a rough lava surface, with all the shadows giving the region a darker appearance. This rough lava is surrounded by smoother lava with abundant inflation features. In volcanology, inflation is the process where the solidified lava crust is lifted by liquid lava being injected into the interior of a lava flow. The inflation features are best developed in the southern portion of the image. Opportunity rover on Valentine's Day, 2014. This is the latest HiRISE image of Opportunity rover at Solander Point, where it spent a few weeks investigating Pinnacle Rock, the so-called jelly donut that was flipped over by the rover wheel. We planned this image when this new rock was first seen. One hypothesis was that a recent impact deposited the rock. We see no obvious signs of a very recent crater in our image, but a careful comparison to prior images might reveal subtle changes besides the rover position. Changes in this region of Mars might be most likely from the action of wind. There are active sand dunes on the floor of Endeavour Crater, but new impacts could occur anywhere. Linear ridges. Straight and meandering thin ridges are periodically found on Mars. Such ridges can form in a variety of ways. Rivers beneath glaciers can deposit rocks and sand, leaving a raised ridge, called an esker, when the glacier retreats. Sometimes sandy riverbeds can become cemented by minerals. Later, when the river is gone and the uncemented soils next to the old riverbed are eroded more easily, the old riverbed itself is left standing. In this observation, relatively straight and narrow ridges are found crisscrossing the slopes between rocky mesas and adjacent valleys. That these ridges extend along steep slopes is unlike the waterborne ridges mentioned above. Additionally, some ridges appear to connect through the mesa and extend also down the opposite slope. These features of the ridges suggest that they cut deep into the interior of the mesas. A ridge of volcanic rock called a dike occurs when magma is squeezed into a deep fracture in the surrounding rock and upward to or near the surface. This magma cools and solidifies into a strong rock that resists erosion better than the fractured rock the magma squeezed into earlier. When erosion of these rocks occurs, the harder volcanic rock is left standing as a ridge and reveals the underground plumbing system of the volcanic vent. Flows in Hellas Planitia. Hellas Planitia is the interior of the Hellas Impact Basin and is one of the largest visible impact craters in the solar system. Hellas is located in the southern highlands and formed very early in the planet's history. The floor of Hellas includes the lowest elevations on Mars and some of the strangest landscapes. The most striking feature of this observation are the incredible banded features, probably due to the flow of surface material. Although Martian flow features may have Earth analogs such as rock glaciers, it's uncertain as to what types of fluvial, glacial, and mass wasting processes are involved in their formation. Fall frosting. Richardson Crater is home to the sea of sand dunes. It was fall in the southern hemisphere when this image was acquired, and the dunes are frosted with the first bit of carbon dioxide ice condensed from the atmosphere. As the season turns to winter, ice will cover the entire dune field. At this moment, however, it is patchy, and then the frost does not yet coat the ground beneath the dunes. The ground under the dunes appears to be cut by spidery troughs termed arenaeform terrain, carved by carbon dioxide sublimation, turning from solid to gas in the spring. Though Mars may appear to be a frozen wonderland, it is not frozen in time. The spring will bring lots of activity to this region.
This image shows an exposure of the North Polar layer deposits with strange streaks superimposed on the layers. These streaks may be formed by winds blowing bright water frost over the surface, removing frost from the surface, or blowing dark material over the frost. These streaks make it a bit more difficult to see the angular unconformity running from upper left to lower right. The unconformity can be traced by finding where the layers at the top of the image are truncated by the layers at the bottom of the image. This relationship shows that the layer deposits were eroded in this area, probably thousands to millions of years ago, before younger layers were deposited over them. The streaks over them were formed during the current northern summer and may not persist for long.
Nergal Vallis tributaries. Nergal Vallis is one of the largest and longest valley networks on Mars, approximately 400 kilometers in length, oriented roughly east-west and located north of the Algiers Impact Basin. Its western region contains numerous short theater-headed tributaries that merge into a long, sinuous and deeply entrenched main valley that extends eastward to Uzboy Vallis. The area in this image is of the westernmost tributaries. Valley heads are steep and abrupt with blunt terminations. Although Nergal Vallis formed long ago, likely by flowing water, abundant wind-blown sediments transformed into the dune fields that now line the valley floors. However, the distinctive valley pattern shape with steep walls and flat floors led many to propose that groundwater flowed out to the surface along the valley heads and walls of the numerous tributaries. This process, known as sapping, begins with groundwater flowing along subsurface fractures or permeable layers and carrying out sediments with it as it emerges at the cliff face. Eventually, the loss of support from beneath undermines the cliff face, causing it to slump into the valley. With continued sapping, tributaries grow progressively in a headward direction. This kind of erosion is common in the Colorado Plateau of the southwestern United States and helped form the distinctive shape of the Grand Canyon. Wrinkled ridges intersecting several tributaries may have provided additional avenues for groundwater flow into the valley system.
Dust-covered channels on Tharsis Tholus. Tharsis Tholus is one of the smaller shield volcanoes on Mars' massive Tharsis rise. The main shield is covered by a very thick blanket, or mantle, of loose material. This is likely to be the same dust that is found across all of Mars. It accumulates on the tall volcanoes because the thin atmosphere at these elevations has a very hard time moving the dust after it is dropped out from the global dust storms. But another reason for the great thickness of the mantle here could be volcanic ash derived from the volcanoes themselves. The flanks of Tharsis Tholus are cut by large channels, similar to those visible on other Martian shield volcanoes like Arceum Mons and Elysium Mons. Like the channels on those volcanoes, these channels probably formed by a combination of erosion by flowing lava, and the collapse of the volcano under its own weight. However, because of the thick covering, we cannot say this definitively. A striking feature at the northern end of this image is the fact that the dust cover is much thinner on the lava flows that surround the shield. This indicates, 1. The surrounding lavas are much younger than the shield, and 2. The mantle on the volcanoes is old.
Polar cliffs and falling blocks. There is an ice sheet at the North Pole of Mars that is a few miles thick at its center. In some places, like in this image, it ends in steep cliffs that can be about 800 meters high. The slopes of these cliffs are almost vertical, which causes slab-like blocks of ice to break off and crash down to the surrounding plains. Dense networks of cracks cover these icy cliff faces, making it easier for these blocks to break free. We've seen new debris at the base of many of these cliffs appearing between successive HiRISE images, so we regularly monitor sites like this to check for new blocks that have fallen. Understanding how these cliffs are formed helps us understand the climactic record stored in the ice sheet itself. Fading impact crater. This cluster of craters formed quite recently from a weak impactor that broke apart in Mars' thin atmosphere before smashing into the surface. It was discovered by the MRO Context Camera team, who found a dark spot in a CTX image taken in August 2008 that was not present in earlier Mars Odyssey mission Themis images from July 2005. HiRISE examined the feature in October 2008 and verified that the dark spot was impact ejecta excavated from beneath the bright surface. On June 25, 2012, HiRISE took another look at the young crater to see how it had fared after 2 Martian years. This image was timed to closely match the illumination and viewing conditions of the earlier HiRISE image. A comparison of the 2 images shows that the dark halo surrounding the crater cluster has nearly vanished. The delicate rays extending beyond the halo are also significantly faded. Only the individual craters remain distinctly dark in the new image. This observation is important for 2 reasons. First, it raises questions about the Martian winds and sediments that produce such changes. Did the dark ejecta blow away, or was it buried by a layer of bright dust? Second, it tells us that the window for detection of these young craters can be very short. In this case, the dark spot that drew the attention of the Context Camera team was the 200-meter diameter halo of ejecta that encircled the crater cluster. After 2 Martian years, the halo is gone, and the impact cluster would not be easily detected. Changing Mars. This image of a wind streak monitoring site northwest of Uranus Tholis shows dramatic differences from the earlier images and evidence for 2 distinct processes of Martian wind erosion. Located near the northern end of the Tharsis Rise at a moderate elevation, the site is in a region of high albedo and low thermal inertia that suggest a thick mantle of dust. Some of the changes that have occurred since the site was last imaged in January 2009. Bright dust has been scoured from the surface by strong southerly winds. Bright streaks trail downward from impact craters, protected from the wind in the lee of the crater rims. Sharp, dark streaks edged upwind as the dust was stripped away. At least 2 different episodes of erosion with slightly different wind directions can be inferred from the orientations of the dark streaks. Yet another wind direction is indicated by the few dune-like ripples that can be seen in the floor of the valley. These features were shaped by much older winds that were probably controlled by local topography. Looking closer at the image, we see a second erosion process, the tracks of dust devils across the newly cleaned surface. What makes these tracks interesting is that they are bright. Most dust devil tracks on Mars are dark, forming when a whirlwind lifts bright dust off the surface and exposes a darker substrate. These tracks were not visible in the image taken previously, nor in an earlier image acquired in January 2007. The cause of the bright tracks is unclear. Bright dust devil tracks were also spotted by the Mars Orbital Camera in southern Schiaparelli crater, a region also dominated at the time by wind streaks. One way to make bright tracks would be to excavate through dark material, such as a lag of basaltic sand, to a brighter substrate. Another possibility is that the dust devils stir up the remaining pockets of bright dust that are hiding from the prevailing winds in the shelter of topographic obstacles. Expanded craters on icy terrain. The middle of this image contains a cluster of depressions with two levels. A small inner crater surrounded by a shallow depression extending outward from the inner crater. This image is located at 50 degrees north latitude, where shallow ice has been mapped by the Mars Odyssey spacecraft. MRO has detected newly formed impact craters in this broad region that expose shallow ice, and also revealed that it is nearly pure ice. One interpretation of the expanded craters visible here is that a group of small impacts, probably secondary craters from a much larger primary crater, exposed the clean, shallow ice in this region. Once exposed, the ice is unstable and sublimates, or passes directly from ice to gas, and the shallow depressions could gradually expand. Colorful surface near Neely Fosse. An enhanced color image of this observation shows a surface with diverse colors just southwest of Neely Fosse. The color diversity of this mesa suggests that the surface has a varied composition, perhaps recording chemical processes of ancient Mars. Much of the surface shows a chaotic mix of colors, but the northern impact crater exposes distinct layers. Different layers have different colors. There are several possible reasons for this. The events that form the layers could have drawn material from different sources, or the layers could have been altered differently after they formed, for reasons such as varying porosity. Sedimentary layers in West Candor Chasma. West Candor Chasma in central Valles Marineris contains some of the thickest of the fine-grained layered deposits on Mars. We can't see the grain sizes with HiRISE, but as the material erodes in the wind, it disappears, apparently carried away by the wind, so the grains must be small. The layers may have been deposited from wind-blown materials, fall of volcanic sediments, or carried in by water, or all of the above. Subsequently, the layers may have been altered by groundwater, producing hydrated minerals such as sulfates. The enhanced colors are related to the minerals or to overlying dust or sand. The dark blue sharp-crested ridges are sand dunes. Rafts of lava with strange infrared properties. This image covers part of the Athabasca Vallis flood lava, the youngest large lava flow on the surface of Mars. At this location, there are two rafted pieces of lava crust with strange infrared properties. Compared to the rest of the lava flow, these two raised areas are cold at night and warm in the day. This property of the surface, where the temperature changes quickly, is called low thermal inertia. Rocks tend to have relatively high thermal inertia, so this is unexpected. This image confirms speculation from earlier low-resolution images. The rafts are composed of broken-up lava, forming an extraordinarily rough surface. Normally, such a jagged pile of lava rocks would have high thermal inertia, but in this location, the rough surface has served as a trap for wind-carried dust. Thus, in these rafts, and only in these rafts, is the lava covered by a thick pile of fluffy dust. Such dust is extremely insulating, meaning that all the solar heating is deposited in a very thin layer near the surface. Therefore, dust gets relatively hot during the day. Because the heat is deposited so shallowly, it is easily lost at night. So the trapped dust is the explanation for the low thermal inertia of these lava rafts. Streamlined hills in Elysium Planitia. This observation was taken to investigate the topography of hills that were eroded by floods of water or lava. In many locations near here, it is clear that the last fluid to flow through the region was lava. Clear margins of lava flows are visible, as well as lava textures on the channel floor. In this location, the cover of wind-blown sand and the effect of many small impact craters has erased such obvious indicators of lava. This is likely because the lava coating is thin and can be easily erased. However, it is also possible that no lava passed through this location. Further investigation of these data should help us better understand the role of water and lava in changing the Martian landscape. Crater with trough in Utopia Rupes. Does this observation show a possible proto-pedestal crater? This crater has a ring trough, but the inner circle around the crater does not appear significantly elevated. Why did the ring around the crater collapse before anything else? Could it be an example of ice sublimating from below the surface? An enigmatic feature in Athabasca lava flows. What is this enigmatic landform? The circular feature is nearly 2 kilometers wide. It looks like a circular island surrounded by a sea of smooth-looking lava flows. The Athabasca region contains some of the youngest lava flows on Mars. Therefore, it is highly possible that volcanism played a role in creating this feature. Perhaps lava has intruded underneath this mound and pushed it up from beneath. It looks as if material is missing from the mound, so it is also possible that there was a significant amount of ice in the mound that was driven out by the heat of the lava. There are an array of features like this in the region that continue to puzzle scientists. We hope the close inspection of this HiRISE image and others around it will provide some clues regarding its formation.
The North Polar region of Mars is capped with layers of water ice and dust called the polar layered deposits. This permanent polar cap is covered in the winter with a layer of seasonal carbon dioxide ice. When the sun rises in the spring, the steep edges of the polar layered deposits are the first to warm up. The dry ice sublimes, going directly from a solid to a gas, and destabilizes loose chunks perched on the steep cliff. Material from the weaker layers gets dislodged and cascades down the steep slope. Here we can see a dark streak marking the path of that loose material, approximately 1 kilometer wide. HiRISE images often show avalanches in progress in the springtime along the edge of the polar layered deposits in this area. This is Phil Plate reading a caption for HiRISE.
Sand dunes in spring. Mars' northernmost sand dunes are beginning to emerge from their winter cover of seasonal carbon dioxide ice. Dark, bare south-facing slopes are soaking up the warmth of the sun. The steep lee sides of the dunes are also ice-free along the crest, allowing sand to slide down the dune. Dark splotches are places where ice cracked earlier in the spring, releasing sand. Soon, the dunes will be completely bare, and all signs of spring activity will be gone. Sandstone cliffs and hematite lag deposits of Ophir Mensa. This target was one of the first close HiRISE views of the enigmatic Valles Marineris interior layered deposits. These light-toned sedimentary deposits are of interest to scientists because they are partially composed of minerals like hematite that likely formed in the presence of liquid water. The lighter-toned linear units to the north are called yardangs and formed when downslope winds carved the fragile sandstone into channels. Over time, wind and gravity conspire to erode material downslope and onto the canyon floor. The darker-toned sandy deposits at the cliff base contain high concentrations of hematite, along with basaltic or volcanic sand, known from infrared orbital measurements. HiRISE resolution can clearly show outcrops mass wasting finer materials out, and darker layers that are likely hematite-bearing units. This is an excellent candidate for what's called a hematite lag deposit, where more resistant iron-rich hematite concretions have weathered out of the brittle Mensa, driven by gravity and wind, similar to that observed at the Mars Exploration Rover Opportunity landing site.
Hydrated sulfate landslides in Ophir. Giant landslides in Ophir host a variety of geologic surfaces and mineralogies. Some possess a variety of hydrated sulfate minerals that formed in the presence of partially acidic liquid water. This image of an ancient, approximately 3 billion-year-old landslide shows two distinct surface albedos, which are proportions of reflected light. These different toned surfaces also mark a transition from one sulfate mineralogy to another and variations in surface evolution. The upper slopes to the north are light toned due to an abundance of hydrated sulfate minerals and bright surface dust. The surfaces that make up the southern portions of the landslide are darker in tone due to the greater frequency of dark sediment that forms strings of sand drifts. Additionally, the underlying units of bedrock consist of darker minerals with less hydration than those to the north, implying a change in the ancient aqueous environments that formed them.
Possible impacts from MSL hardware. This cluster of small impact craters was spotted by the context camera on the Mars Reconnaissance Orbiter in the region northwest of Gale Crater, the landing site of the Mars Science Laboratory MSL rover Curiosity. We had suspected that the cluster was produced by the impact of MSL's hardware onto the surface of Mars, because we could see it in context camera images after the landing, but it was not present in images prior to the arrival of MSL. Consistent with this interpretation is the fact that the cluster is located along a line between the Curiosity landing site and a strewn field of debris previously identified in HiRISE images as being caused by MSL hardware, in particular the cruise stage and/or tungsten weights used as cruise balance masses. Over a year has passed since the landing, so this impact cluster is not as fresh as those imaged earlier and has been degraded somewhat by winds from the northeast. Nevertheless, the cluster shows some similarities to the impact's uprange, including asymmetric ejecta patterns that indicate an oblique impact. The cluster is located some 9 kilometers downrange of the impacts imaged earlier, about 70 kilometers away from the rover landing site. With a close-up image, we see that it was produced by a shotgun blast of at least 40 individual impacts that formed small craters no larger than 2 meters in diameter. In contrast, the uprange impacts included 4 craters that were 4 to 5 meters in diameter. Assigning each of the impacts to specific pieces of hardware is a challenging puzzle, but it is thought that the 4 large craters were produced by 2 large tungsten weights that broke in half to make these 4 craters, or by pieces of the cruise stage, which was designed to break up in the atmosphere for planetary protection purposes to kill any earthly microbes. The cluster imaged here adds to the mystery and may have been produced by a piece of the cruise stage that traveled farther through the Martian atmosphere and was therefore more thoroughly fragmented by the time it crashed onto the surface. Slope streaks on a dusty planet. Mars is a dusty place, and in some locations, thick blankets of its characteristically red dust can slowly settle out of the atmosphere and accumulate on slopes. This dust is also a lot brighter than the dust-free terrain on Mars, so if you scrape off the dust, you see a darker surface underneath. This particular image shows one of these dusty areas. The dark streaks on the slopes are locations where the dust has slumped downhill, revealing a less dusty surface underneath. In some cases, these slope streaks might be triggered by Mars quakes or nearby meteorite impacts. Scientists think they form quickly, more like an avalanche than dust slowly creeping downhill. Look more closely, and you'll notice that some streaks are darker than others. Dust is settling out of the atmosphere all the time, and these dark streaks get slowly buried by fresh dust so that they fade back into their brighter, redder surroundings. It's not certain how long this fading takes to happen, but it's probably close to a few decades. Dust is an important player in the weather and climate on Mars. Images like this are used to monitor slow changes in these streaks over time to better understand how much dust is settling on the surface. Mysterious light-tone deposit in Vinogradov crater. Vinogradov is an old 224-kilometer diameter heavily degraded impact crater in southern Margarita Terra. The southeastern floor of Vinogradov is covered with several mysterious light-tone submeter scale blobs that lack obvious layering. In some places, the light-tone material appears to have pre-existing craters, giving them a circular appearance. The light-tone material has a northwest-southeast orientation and tends to be associated with a smooth, darker-toned deposit. This material may be related to ejecta from a nearby crater, eroded from the rim of Vinogradov, or emplaced by some other process. Opportunity rover's winter work at Murray Ridge. This HiRISE image of the Opportunity rover was acquired as a coordinated ride-along observation with the CRISM instrument, which is also on board the Mars Reconnaissance Orbiter. The CRISM instrument is a spectrometer that views the surface in many wavelengths beyond what the human eye can detect, allowing for mineral identification of the Martian surface. HiRISE images can be used to construct digital terrain models, or DTM, like the one we made of Endeavour Crater's western rim, which provides high-resolution topography for landing site support. This southward perspective view was built using that DTM. The use of CRISM mineralogy, along with topography and fine-scale images from HiRISE, will aid in Opportunity's investigation into the geologic history of the Murray Ridge of Endeavour Crater. A heart in Ascraeus Mons. What is this strange-looking feature? HiRISE scientists first noticed it in images from the context camera and acquired this picture to investigate more closely. The feature indeed does look like a heart. It is located south of Ascraeus Mons, which is a large volcano within the Tharsis volcanic plateau. So it is extremely likely that this feature was formed by a volcanic process. The feature rises above the surrounding terrain, and we can see concentric ridges on its top. Perhaps this feature is an ancient vent structure, an opening in the ground from which volcanic lava emerges, that has been more resistant to erosion than the surrounding area, so that it resembles inverted terrains. Topographic inversion or inverted terrain often occurs when low areas of a landscape become filled with lava or sediments that harden into materials which are more resistant to erosion than the materials that surround them. Differential erosion then removes the less resistant surrounding material, leaving behind the younger resistant material, which may then appear as a ridge where previously there was a valley, or in our case, a butte where there was once a pit or depression. Additional imaging of the feature to create a stereo and a digital terrain model may help in further assessing the structure by making accurate measurement of its height and the steepness of its slopes. Slumping terraces on a crater wall. This image shows the western rim of a well-preserved 8.5-kilometer diameter impact crater. The wall features a slumped terrace that extends all the way around the crater diameter. This slumped terrace, a result of the crater formation process, gives the crater a concentric ringed look. Terraces are an expected feature in Martian craters of this size or larger, as the original material strength of the surface is overcome by the force of all of the sudden missing mass. Blocks of rock slump down the steep crater walls and slide inward. By contrast, terraces in smaller craters are often the product of the impact of an object into a surface with layers of differing material strength.
Two-color dunes in Meridiani Terra. Why are these dunes different colors? Sand on Mars is typically dark in tone, as it's commonly derived from volcanic rocks like lava flows. In enhanced color, surfaces like these dune crests are dark blue to purple. Sand comes in sizes that are ideal for surface transport by the wind, where sand hops along, creating bed forms like these dunes after large amounts of time. The lighter-toned tan or reddish surfaces are indeed composed of a different material, but not sand-sized particles that make up the bulk of these dunes. Rather, the light-toned smooth surfaces that dominate the lower, flatter areas of the dunes are a thin coating of global dust. Dust on Mars is composed of a variety of materials, including oxidized iron, like rust. For a given wind gust, speeds are not constant at different heights. Rather, wind speeds are greater with height above the ground, and wind energy drops to nearly zero at the surface. Dust persists on flatter dune areas because wind energy there has not been sufficient to remove it, whereas dust-free higher-lying dune crests are subject to more intense winds, which ultimately conspire to make the appearance of two-color dunes.
Ring of cratered cones. In the center of this observation, we see a ring of cones that have developed over a crater rim. Lava appears to have deflated around and within the ring. Interestingly, the area around the ring has few cones. Did water or steam flow to the crater and make that zone less fertile? These cones are likely rootless cones, so named because they do not form as a result of direct magma supply, but from the interaction of lava and water or ice in the substrate. The rootless cones in this image may have formed around the crater rim because the lava was thin there. Rootless cones are also found on Earth, such as the Mýrdalsjökull ice cap glacier in Iceland. Mission 2020, a candidate landing site in Gusev Crater. As we did for Phoenix in 2008 and the Mars Science Laboratory in 2012, HiRISE has been imaging landing sites for a potential rover mission in 2020. With HiRISE resolution, mission teams can examine what areas of Mars are flat enough to touch down safely and also investigate the terrain to satisfy scientific research goals. Gusev Crater, a massive and ancient impact crater, was also the landing site for the rover Spirit in January 2004. With this image, the science rationale was to investigate nearby opaline silica, carbonates, and other aqueous phases. An irregular crater intersecting Graben in Tractus albus. This crater, of which only a small portion is visible in the full HiRISE image, is very irregularly shaped and might suggest that some underlying liquid was present that made it so elongated after the initial impact. Another reason for the crater's shape might be that it was caused by a binary asteroid pair, or a meteorite that broke into multiple fragments just before hitting the ground, leading to the formation of a number of superimposed craters that produced this odd-shaped depression. The crater itself intersects a graben, which is a depressed stretch of land typically bordered by parallel faults. Note the dark streak on the crater's eastern wall. An elevated crater in the Apollinaris Mons region, volcanic or impact-related. Impact craters are very common on the surface of Mars. However, when a circular depression is visible on the summit of a mound or an elevated landform in general, careful analysis is needed to identify whether the crater is created by an impact or by volcanic activity. This issue becomes even more problematic when the crater is located in an area known for its volcanic history, such as the Apollinaris region, where this image was taken, and is very close to the prominent volcano, Apollinaris Mons. In fact, this classical problem has been encountered before here on Earth, in the case of the famous Meteor Crater in Arizona, just outside the city of Flagstaff. Back in the late 19th century, many people believed that Meteor Crater was a volcanic crater because of its proximity to the San Francisco volcanic field and the rarity of impact craters on Earth. Meteor Crater remained controversial until the 1960s, when scientists were finally able to confirm that the crater was indeed an impact crater by identifying minerals in the crater site that can only form in extremely high pressures, which are usually associated with violent impact events. We can see in this image that the crater is on the summit of a mountain or hill-like elevated landform. In addition, some of the materials at the base of this elevated landform exhibit a rough texture that may resemble volcanic flows. If we add to that the region is within a volcanic area, it becomes highly likely that this crater in particular is in fact a volcanic crater. Dark-toned pitted mound in a crater in northeast Arabia Terra. This fascinating observation shows us a dark-toned mound with pits inside an impact crater. Are these pits the result of sublimation? The crater itself is an ancient one, as evidenced by the eroded rim. For the mound inside, HiRISE resolution can give us a closer look at textural features that might help explain what we're looking at. Layers in pit walls, or perhaps cracks from expansion. A large banded angular fragment in Nili Fosse. In a context camera image, there is a large angular fragment that appears to have light and dark-toned bands. HiRISE images of similar fragments nearby also show this banding, and the resolution of our camera may help determine what these layers are. Nili Fosse was once considered a potential landing spot for the Mars Science Laboratory and is one of the largest, most diverse exposures of clay minerals. Clay minerals contain water in their mineral structure and may preserve organic materials. An unusual mound. With its cracked, blistery appearance, this mound near the center of a very large, over 5-kilometer diameter mid-latitude crater poses an interesting question. How did this form? More importantly, what is the relationship between the mound and the surrounding viscous features? Did those flow features play a role in forming the mound? Can that material help explain the cracked surface of the mound? Bedrock in a trough in Asimov Crater. This image was acquired in southern winter over part of Asimov Crater, showing the equator-facing slope of a deep trough inside the crater. The crater appears to have been completely filled by a thick sequence of materials, perhaps including sediments and lava flows. Later, deep troughs formed around the outer edge of the fill material, probably by collapse over void spaces at depth. What made the void space is not known, but one idea is that there were lenses of ice that slowly sublimated into the atmosphere. Another idea is that this is part of a sequence of crater fill and exhumation that includes Gale Crater, the home of Curiosity rover. In other words, continued collapse and erosion of Asimov Crater could eventually lead to a central mound like Aeolus Mons, popularly known as Mount Sharp in Gale Crater. However, at Asimov Crater, the southern trough has destroyed the southern rim of the original crater, which didn't happen at Gale Crater. Many of these steep trough slopes in Asimov Crater, where facing the equator, have recurring slope lineae, or RSL, activity in the summer, when the sun-facing slopes get warm. The RSL fade in the winter, so none are visible in this image even if they were present last summer. There are no previous HiRISE images acquired in the summer over this location. Asimov Crater was named after Isaac Asimov, professor of biochemistry and prolific writer of science fiction and popular science books.
This observation shows dunes in the Martian North Polar Sand Sea in the process of defrosting. Every winter, dunes and other surfaces at these northern latitudes are coated with several tens of centimeters of carbon dioxide frost and ice, plus a minor amount of water frost. The white material is fine-grained frost. The dark, splotchy tones on the dunes may be deposits of particulates deposited from carbon dioxide geysers or relatively thick deposits of carbon dioxide ice. The more brownish colors represent defrosted areas. Polygonal patterns on the surface of the dunes are probably cracks in overlying carbon dioxide ice.
Near the mouth of Morava Vallis. Morava Vallis drain Ladon Basin and discharge towards the large regions of chaotic terrain near the head of Ariz Vallis. Because the valley emerges full bore from Ladon Basin, much like the Niagara River emerges from Lake Erie on the Earth, it has been hypothesized that it was formed when a lake overflowed the basin. There are numerous valleys, including the large Ladon Vallis, that end along the margin of Ladon Basin. Some of the outcrops visible in this image and elsewhere in the basin show evidence of layering due to deposition of sediments. Comparison of the nature and extent of layers exposed here and elsewhere around Ladon Basin should help to constrain their origin by water flow or other processes. Different materials exposed along a wall rock slope in Koprates Chasma. This image shows several kilometers of topography exposed along the wall rock within Koprates Chasma. There are patches of brighter materials exposed within the wall rock and along the chasma floor. The bright massive rocks exposed in the wall rock likely represent weathered rocks that have altered to this brighter material. Lower down the wall rock and along the chasma floor, the brighter material appears layered and could represent sediments deposited within the chasma when water or ice may have existed here. The image also shows finer material composed of eroded wall rock and aeolian debris that is mass wasting downslope. Ejecta in excess. When impact craters are formed, the material that once resided in the subsurface is blown upward and outward. This material falls back and settles around the newly formed crater into what is called an ejecta blanket. It often appears as a layer on top of the original surface extending radially outward from the crater. In some cases, the volume of the ejecta material, mainly rocky debris, appears to exceed the volume of the original crater, presenting something of a puzzle. One hypothesis is that the original surface may have been inflated with an ice-rich layer at the time of the impact. After the impact, the newly formed blanket of ejecta then protected this ice from evaporation loss, while the rest of the surrounding terrain was unprotected and deflated as ice was lost due to the more recent climate changes. Examining these craters up close with HiRISE may reveal clues to the presence of buried ice deposits today beneath the ejecta and about the subsurface stratigraphy exposed along the crater walls. Craters within craters. Sandwiched between a crater nearly 4 kilometers across and a much larger and older crater over 15 kilometers in diameter is this small impact crater with light-toned material exposed in its ejecta. Because the material is still brighter than the surrounding surface, darker dust settling out of the atmosphere has not had time to cover it up, so the crater is fairly recent. Of course, recent could mean on the order of thousands of years or older. This small crater is also fairly shallow and smooth in its interior. This light-toned rock deposit is also visible along neighboring scarps and even in the rock strata exposed along the rim of the larger 15-kilometer crater, indicating that the formation of this rocky strata predates all of these craters. The brightness and color of these deposits are the result of different minerals within the rock relative to the nearby darker rocks and soils, and perhaps indicate extensive chemical interaction between water and the native rocks. A complex valley network near Ideas Fossae. Many valleys occur all over Mars that reveal an extensive ancient history of liquid water erosion. While these valley systems are typically now covered with fine soils and sand dunes, the overall scale and shape of the valleys reveal much about the ancient climate. The speed, volume, and extent of the flowing water can be apparent from how it interacts with obstacles. For example, large volumes of rapidly flowing water may overtop obstacles rather than being diverted around them, or a small stream flowing for an extended period may gradually cut downward through hard rock obstacles. In this case, the valleys cut through a small kilometer-sized impact crater. As it did so, the flow appears to have divided it into as many as 3 streams and then coalesced as it exited the other side. Dramatic dune destination. This image of a sand dune field in a southern highlands crater was acquired when the sun was just 5 degrees above the horizon. As a result, the image is mostly shadows, with sharply delineated dune crests sticking up into the sunlight. The especially bright patches, bluish in enhanced color, are due to seasonal frost that is accumulating as this hemisphere approaches winter. Don't get lost in the North Polar ice cap. A bright ice cap of frozen water covers the North Pole of Mars. In the winter, thin coverings of carbon dioxide and water frost covers this area, and these frosts finally disappear at the end of the Martian spring season. In this image, the winter frosts are about to disappear, and we can begin to see the surface features of the ice. The ice cap would be a bad place to get lost. It's one of the smoothest, flattest places on Mars, so there are no visible landmarks. The surface features are gently rolling small mounds and hollows, about 1 meter in height and about 20 meters across. This monotonous landscape continues for hundreds of kilometers in every direction, with the same repeating pattern. Scientists do not know what makes this pattern so uniform over such large distances. We acquire HiRISE images like this one to look for small differences in these icy features from one place to another. Understanding the surface can help us understand the current climate and meteorological conditions at the North Pole of the red planet. Many small interesting ridges in Erythrea fossa. These light-tone ridges are found in a large fracture located east of Holden Crater and form a curious box-like pattern. A hairline fracture runs along the axis of each ridgeline. The overall pattern spans several hundred meters across, and individual ridges are several meters wide. Scientists are not sure how they formed yet, but some possible explanations suggest that mineral-rich groundwater flowed out of the hairline fractures and deposited minerals at or near the surface as the water evaporated. In addition, these minerals may have formed a cement along the fractures, making these patterns more resistant to subsequent erosion by wind or other processes. The resulting cemented ridges then stand high above the surrounding plains. A crater straddling two terrain units. An approximately 1 kilometer impact crater located in northern Sinus Meridiani has formed along the boundary of two different terrain units. The western part of the crater has formed along a unit consisting of wind-blown basaltic materials that overlie light-tone units exposed in the crater wall. To the east is a shallow circular depression several kilometers across that consists of multiple layers of light-tone deposits that have been eroding away. These deposits are bright in Themis nighttime infrared and dark in daytime infrared images, suggesting that they are relatively fine-grained and largely devoid of rocky materials. Dark, fine-grained basaltic wind-blown material partially mantles these units and forms dunes throughout the region. Along the eastern rim region, the impact crater is eroding back into the terrain, forming scalloped inlets in the crater rim and re-exposing the multiple layers of light-tone deposits. Terracing is common along the eastern slope of the crater. Turning our attention to the western slope, we see that the rim is eroding back into the terrain more evenly. Although this slope lacks a scalloped appearance, the erosion of the top units appear to be more even and at a faster rate than the underlying light-tone deposits. Dark wind-blown basaltic dunes line the floor of the crater. Some possible explanations for the origin of these light-tone deposits are that they are altered volcanic ash or ancient lake deposits. Curiosity trekking. Curiosity has been on the move. In this most recent HiRISE image of the MSL rover, the tracks are visible from Yellowknife Bay to its location on December 11, 2013, several kilometers to the southwest. Tracks from its landing site to Yellowknife Bay, made more than a year ago, are faded but still discernible. The enhanced color image shows where the tracks cross the narrow, 1 kilometer wide color swath of HiRISE. A black and white sub-image shows the rover itself. Rather than follow a straight path to its next destination, the rover has zigzagged to avoid steep slopes. Curiosity is progressing from the bright dust-covered area to a region with a darker surface, where saltating sand keeps the surface relatively free of dust. The scenery seen by the rover will be getting more interesting as it progresses toward Mount Sharp. Sculpting dunes in Ganges Chasma. When dunes are located in a complex topographical area such as a canyon, they become ideal candidates for detecting changes to their shapes and sizes over time. The dunes here in Ganges Chasma, a canyon that's on the eastern end of Valles Marineris, could be strongly influenced by winds, and it's important not to underestimate the erosional power of wind. Because HiRISE has such good resolution, we can track these changes over time to tell us which way a dune is moving. From these observations, we can decipher present-day atmospheric processes. Equatorial gullies. Gully-like landforms, or ravines, are most common in the middle latitudes of Mars, but also occur in the polar and equatorial latitudes. We see here an impact crater about 900 meters wide, with distinct gullies on all inner slopes except in the northwest sector of the crater. The crater formed on the side of an ancient channel, so the northwestern section slumped into the channel, so the slopes are not as steep. This region of Mars is called Libya Montes, near the equator on the south edge of the Isidis impact basin. These are typical gullies with alcoves at the top, channels, and depositional fans at the bottom, but the alcoves are relatively small compared with many other mid-latitude gullies. HiRISE has shown that gullies are actively forming today in the southern mid-latitudes, aided by the seasonal deposition of carbon dioxide frost, or dry ice. The equatorial gullies here appear pristine, with no superimposed craters or wind-blown deposits, so the gullies formed in the recent past and could still be forming today. Here in the Martian tropics, it is too warm for dry ice to help fluidize the movement of debris, but the slopes are probably steep enough for dry particles to move, perhaps aided by water in the crust to reduce friction. Frost in dune shadows. This southern autumn image captures a view of frosty dunes. The sunlight is shining on the dunes from the upper right. The low sun angle creates large shadows from these dunes, making for a dramatic picture. Frost is visible in the shadows of the dunes that appear as lighter, bluer swirls in each shadow. Along the illuminated section of the dunes, 5 dark, thin dust devil tracks are snaking their way along, parallel to the dune ridge. Dunes streaming through hills. This dramatic image shows dark rippled bodies of sand, sometimes in the form of dunes, streaming through Ganges Chasma. The floor of the canyon is covered by hills and mesas, perhaps remnants of chaotic terrain that formed from sudden collapse as water was withdrawn to form outflow channels. The sand moving through, generally from east to west, interacts with the topography to make streamlined shapes. A close-up image in enhanced color shows one hill with a dune piling up to the east. Craters in an icy surface. Small impact craters usually have simple bowl shapes, but sometimes more complicated shapes can occur if the target is unusual. The crater in the center of this HiRISE image is unusual because there is a wide, flat bench or terrace between the outer rim and the inner section, making it appear somewhat like a bullseye. Crater shapes like this can occur if material underground changes from weak to strong. In these cases, the level of the terrace shows where this change occurs. In the area covered by this observation, we have other reasons to suspect that the upper material is mostly ice. Terrace craters like this one show us how thick this ice is, as the terrace formation shows us where the ice meets the underlying rock. Recurring slope lineae in Copertes Chasma. Recurring slope lineae, or RSL, may be due to active seeps of water. These dark flows are abundant along the steep slopes of ancient bedrock in Copertes Chasma. The RSL are most prominent on the bright fans at the base of the bedrock, but actually extend back into the bedrock following small channels. MRO is continuing to monitor key sites to better understand this and other geologic activity on Mars. Finding faults in Melas Chasma. Melas Chasma is part of the Valles Marineris Canyon system, the largest canyon in the solar system. It's been recently suggested that melaschasma may have been produced by an impact crater. To test this idea, HiRISE has been imaging surrounding small faults, such as the one seen in this image. There are actually 3 faults in this image. The 2 trench-like features are called graben and are caused when the surface stretches apart and blocks of rock drop downwards. The 3rd fault is the wavy ridge that cuts across both of the graben. This type of fault is sometimes called a wrinkle ridge and occurs when surface rocks are compressed, causing one block of rock to be thrust up on top of another. So this area has been both stretched in the north-south direction and squeezed in the east-west direction. With enough HiRISE images, scientists hope to reconstruct the full history of this area and uncover the origin of one of Mars' most spectacular features. Terrain near the MSL landing site. This image is of a region slightly to the southwest of where the MSL rover, called Curiosity, will land in August 2012. It shows 3 distinct terrains: older plains, an overlying unit with a distinct margin, and recent sand dunes. The dunes indicate that the strongest winds tend to blow from the southwest toward the northeast, and, like many dune fields on Mars, are probably moving slowly. The second unit has a margin that, at low resolution, is similar to a lava flow. It also has a hard surface that retains impact craters better than the older plains beneath it. At full HiRISE resolution, it is evident that this deposit is not lava. It has thin layers and a dense network of fractures across its surface. The tops of some lava flows and lava lakes are also fractured. However, HiRISE has confirmed that the size and other characteristics of lava fractures are quite different from the ones visible here. Hence, this is some kind of sedimentary deposit, possibly consisting largely of hardened mud. It is likely that Curiosity will have an opportunity to investigate terrain like this soon after landing as it drives to the layered mound to the south.
The objective of this observation is to examine what may be formerly ice-rich terrain that has just lost ice to the atmosphere. Research with the shallow radar instrument on board the Mars Reconnaissance Orbiter has found that many areas in Deuteronolis Mensae are glaciers with a thin layer of debris on top of them. This image may show a transition from ice-rich to ice-poor terrain. Removal of buried ice can cause collapse and may be responsible for the strange appearance of this terrain. Understanding the origin of features in this image tells us something about when buried ice was stable or unstable, and therefore helps us figure out how the climate of Mars has changed.
Bright sediments on the floor of Leyden Basin. This image shows some bright layered deposits exposed within a linear trough along the floor of Leyden Basin. There's a large channel system that flows into the basin called Leyden Vallis, and scientists think that the basin may have once been filled with water before another channel to the north formed and drained it. These exposures of light-toned layered sediments provide clues about the environment that existed within Leyden Basin when water may have ponded and deposited these sediments.
There are 3 active dust devils in this image, but they aren't monsters like a previous HiRISE image. Viewed with red-green glasses, the active dust devils seem to float above the surface. There are also some bright lines present in only the later image. Those are the tracks of dust devils that pass through this.
Frosted gully landforms. This image shows a crater wall in the southern hemisphere with gully landforms. Gullies like these are mostly found in the mid-latitudes, between 30 and 50 degrees north or south. In the Martian winter, frost, mostly carbon dioxide, can build up in the gullies, especially on the cold slopes that face the pole. The bright bluish enhanced color frost is clearly visible in the upper alcoves of gullies here. We now know that Martian gullies are active and that most changes occur in the winter. It is likely that frost like this causes the activity in some way.
There are 3 active dust devils in this image, but they aren't monsters like a previous HiRISE image. Viewed with red-green glasses, the active dust devils seem to float above the surface. There are also some bright lines present in only the later image. Those are the tracks of dust devils that passed through this region in the prior 2 weeks.
A crater north of Coppertese Chasma. This image shows a fresh impact crater about 2 kilometers across. How do we know it's fresh? The crater walls are steep and rocky, and fine striated texture is still visible on the ejecta. Over time, erosion and dust settling out of the atmosphere will smooth out such details. However, these processes are slow on Mars, and the crater is probably at least several million years old. Craters like this are important targets for HiRISE for several reasons. The details of the fresh crater are interesting in themselves for studying impact processes. But crater walls can also provide great exposures of bedrock. The steep slopes are also good places to look for active processes like rockfalls happening today, especially when we can compare a series of images taken over several years. Light-toned rocks exposed along Coppertese Chasma. Coppertese Chasma exposes several kilometers of rock that tell scientists about the processes that occurred in the ancient past and in the subsurface. In this HiRISE image, rocks that display several colors and brightness are visible along the chasma wall. Some of the brighter rocks could be minerals that formed when basaltic rock was altered by water flowing deep underground a long time ago, before the chasma opened up. Alternatively, the light-toned rocks may be sediments that were deposited when water filled up portions of the chasma. Dark dunes that could still be active are at the bottom of the image, attesting to more recent activity in this location.
High-altitude clouds on Mars. The standard color images for this observation look really weird. The reason is apparent by looking at an animation of the color images. These were acquired in a particular sequence, first blue-green, then red, then infrared. What we see are thin condensate clouds moving relative to surface features. They appeared to move 200 meters distance over the 0.1855 second between the infrared and blue-green imaging, or 1.08 kilometers per second. Wait, that's supersonic. Can clouds do that? No. The MRO spacecraft also moved 603 meters along its orbit in its 0.1885 second frame, so from 260 kilometers altitude, we have a stereo convergence angle of 0.133 degrees. Such a small convergence angle would be useless for stereo imaging of surface features up to only about 1 kilometer high, but clouds can be much higher. If the clouds were half as high as MRO, or 130 kilometers, they should appear to move 603 meters relative to surface features. Since they only move 200 meters, their heights must be approximately 42 kilometers. Previous imaging experiments have measured Martian clouds up to 80 kilometers in height. High cirrus clouds on Earth extend up to about 12 kilometers in height, but the lower gravitational acceleration of Mars creates a more extended atmosphere. The high clouds on both Earth and Mars are composed of ice crystals, although on Mars they may be from carbon dioxide rather than water.
Light-toned deposits along Coppertese Chasma slopes. Valles Marineris contains kilometers-thick light-toned layered sedimentary deposits along many of its floors. In this image, similar light-toned layered deposits are observed, except these are found along steeper wall rock slopes in Coppertese Chasma. Compositional data from CRISM and also stereo images, which we use to create 3D images, can help scientists determine how these sediments were deposited and if they are the same as the thicker deposits seen along the chasma floors.
Shapes and spots on a polar sand dune. This image shows numerous dark shapes and bright spots on a sand dune in the northern polar regions of Mars. The bright spots are carbon dioxide frost. On Mars, the main atmospheric component is carbon dioxide, which circulates seasonally between the atmosphere and the polar regions. One of the reasons that permit this process is the fact that temperatures on Mars are much colder than on Earth, which allows carbon dioxide frost to condense on the surface in winter. When spring comes, however, the surface heats up, and the carbon dioxide frost eventually sublimates, going directly from the solid to the vapor state, and forms jets of carbon dioxide mixed with dust, leading to the formation of the dark features we see in the image. Such processes occur seasonally on Mars, and therefore are continuously being monitored by the HiRISE scientists to assess the differences from one year to the next. Oxus Patera collapse feature. Oxus Patera is an ancient, eroded depression in northern Arabia Terra. It is not known how Oxus Patera formed, though it has been suggested that the feature represents an ancient caldera formed through collapse and explosive volcanism. Other possibilities include formation by impact and erosion, or collapse due to removal of subsurface volatiles. Regardless of how the massive depression originally formed, there is little doubt that the feature has been modified by younger, ice-related processes. This image shows an unusual landform on the floor of Oxus Patera. Notice an irregular scalloped contact trending diagonally from the southwest to the northeast, near the center of the image. The terrain in the upper left is likely composed of fine-grained, weakly consolidated materials because it does not form many topographic features within the unit, such as mesas, buttes, or mountains. Where it is eroded, it does not form boulders. It appears to be an easily crumbled blanketing deposit. The terrain in the lower right is very unusual. It contains smooth surfaces marked by small, irregularly shaped cones and fractures that are bound by upturned ridges. The boundary between the two terrains consists of scalloped fractures that appear to have formed where the terrain in the lower right has detached from the terrain in the upper left and partially collapsed.
Giant gullies north of the Ariz impact basin. This image shows gullies that are large even by Mars standards, and much larger than the terrestrial landforms we call gullies. The length of some of these is over 6 kilometers, or 3.6 miles. They are located on large mountains north of the Ariz impact basin. An enhanced color view shows only subtle colored differences.
Dunes on the rim of the HiRISE impact basin. Sand dunes like these in this image have been observed to creep slowly across the surface of Mars through the action of the wind. These are a particular type of dune called barchan, which forms when the wind blows in one direction for long periods of time. Barchan dunes are common on Mars and in the desert regions of the Earth. These barchan dunes are located on the western rim of the HiRISE impact basin in the southern hemisphere of Mars. This area is covered by extensive deposits of layered rocks that were initially deposited as loose sediments and over time formed these rock layers. Portions of these layered rocks were subsequently eroded away, and the remaining layers now form numerous flat-topped hills called mesas. The barchan dunes are forming in the lee, or downwind, of the mesas. Careful comparison of repeat images like this one can reveal the speed and manner by which dunes move across the Martian surface. This information can be used to study the current atmosphere of Mars, the age and mobility of sand deposits on the planet's surface, and the hazards that sand dunes may pose to landed vehicles, such as rovers.
Looking for salts on Mars. Why are scientists interested in areas that contain salts on Mars? Simply put, salts usually form by evaporation of liquid water. Most salts can easily dissolve in water, and if the water evaporates away completely, the salt is left behind as a deposit or residue. The larger the amount of salts initially dissolved, the larger the salt deposit left behind when the water evaporates. So when scientists look for regions on Mars that have noticeable salt deposits, they are effectively looking for areas that may have contained liquid water in the past. A few years ago, a group of scientists found more than 600 locations on Mars that may contain chloride salts, which could be very similar to common table salt. Since then, Scientists have been using the HiRISE camera to look at these locations more closely, and they have found out that many of these areas are very similar to dried lakes on Earth, which are sometimes called playas or salt pans. Many such playas can be visited in California and Arizona, such as the Racetrack Playa and the Death Valley National Park. In this image, the chlorides have a bright appearance and are covered by other dark materials. Interestingly, the bright deposits also display cracks that form polygonal patterns very similar to common mud cracks, which may be another indication that these deposits formed when salty waters evaporated away. Studying these regions in detail can help scientists understand when and how the weather conditions on Mars may have changed.
This image shows layered bedrock composed of light and intermediate tone materials. There are also darker bed forms that fill in low-lying topography, such as impact craters. In the center of the image is a valley with darker fill extending from left to right. The darker materials within the valley might be fluvial sediments. At HiRISE resolution, we might be able to decipher the properties of the bedrock, as well as what deposited the sediments. This image near Mars' North Pole was a public image suggestion with the following rationale. My 3-year-old son has dubbed this white smudge Pluvo Point. He thinks we should take a picture of it to learn about how snow and ice comes down on Mars. Although we can clearly see the bright area in this image, it isn't due to frost or ice at this time of year, early summer, and doesn't have the relatively blue color expected for frost. So what does create the white smudge? The image shows a typical region of northern plains covered by polygons and boulders. There are dark areas and low spots that are probably due to wind-blown dark sand. Where the sand is most abundant, it forms the dunes seen near the top and bottom of this image. The white smudge appears to be a region with relatively little dark sand. It isn't actually white, but it is brighter than other nearby regions. These could be low hills where the sand doesn't collect.
Banded ridges in Hellas. Low-lying areas in the Hellas region, which is the largest impact basin on Mars, often show complex groups of banded ridges, furrows, and pits. These sorts of bands suggest that the surface material has flowed and twisted viscously, like taffy. The orientation of the ridges and groups of ridges would then point in the direction of the flow, called streamlines. Making this landscape even more complex is when we see that the ridges are sometimes disconnected. They stop abruptly, break up into blocky segments that sometimes appear offset. Such mixed-up fragments give an initial sense that parts of the flow have been rafted apart from one another. Alternatively, the entire region may be substantially eroded since the time when the taffy-like ridges actually formed. In that case, the flow may have been far more complex and three-dimensional, such that the disconnected portions are actually areas where the flow transitioned up and down relative to the current plane of the eroded surface. In this way, we only see a slice through a far more complex series of twists and bends, some of which is still buried beneath the ground. What this taffy-like material is made of is currently unknown. Hard and soft rocks, as well as ice and ice-rich rocky debris, can deform and flow given time under the force of gravity and the pressures found deep beneath the surface. Afterwards, differential erosion of hard and soft rock or icy materials mixed in bands and layers might give rise to the ridges, furrows, and pits which we observe today. The obliquity of Mars. On Mars, sediment layers of near uniform thickness visible from orbit are a fingerprint of deposits that record many cycles of obliquity change. This HiRISE image of an east-facing slope in Tithonium Chasma was taken to follow up an earlier context camera image that seemed to show sediment layers of near uniform thickness. These sediment layers are the dark and light stripes that run diagonally across the center of the observation. In this top-down view, afternoon sunlight picks out subtle east-west trending ridges in the east-facing slope. The dark and light stripes appear to deflect downslope across the ridges. To a geologist, this outcrop pattern shows that the dip of the ancient sediment layers is gentler than the slope of the modern hillside. Further analysis of the image may determine whether these layers do record ancient obliquity-driven climate change on Mars. Exploring the mounds in Chryse region. The mounds in this observation may have been formed by a process called diapirism, where material at depth is more buoyant, i.e. lower density, than the surrounding rock, so it rises to the surface. Why might this be of interest? At HiRISE resolution, we might be able to study the uplifted material more closely, such as if there are clays or other aqueous materials present. If these mounds were formed by diapirism, it offers a deeper window into the Martian past. This area could also be an interesting site for a future exploration rover. Wavy-looking layers in the North Polar layer deposits. These layers near the North Pole of Mars probably record global climate changes, similar to ice ages on Earth. They appear wavy here either because flat-lying layers have been eroded into shallow valleys and ridges, or because the layers are not horizontal. Some of these layers are truncated or appear to pinch out against other layers, evidence of a period of erosion followed by continued deposition of new layers. The orientations of both the wavy-looking layers and the unconformity, or erosional surface, will be determined once this image and its stereo pair have been used to measure the surface topography. Layers in Flammarion Crater. The objective of this observation is to examine layers. In and around this region, there are outcrops of layered terrain. A high-resolution image can see minute details that will enable us to start to catalog different types of layers and to discover under what conditions they are produced. In this particular image, there is a caprock on top of some poorly formed layers and some well-formed layers. This caption is based on the original science rationale. Dunes on the move. HiRISE has been carrying out a dedicated survey of sand dunes on Mars, determining whether and how fast the dunes move by observing repeatedly at intervals of Martian years. More than 60 sites have been monitored so far, showing that sand dunes from the equator to the poles are advancing at rates of up to 1 meter per Martian year. These observations are still spotty, however, and tend to be concentrated in the tropics and the North Polar Erg, the sand sea that surrounds the North Pole. One latitude band that had not been sampled at all lies between 30 and 65 degrees north. This observation is among a set of images acquired to fill that gap. This observation shows a variety of different dune types in southern Lyot crater in the northern lowlands. Transverse dunes to the west grade into longitudinal dunes downwind to the east, and barkens to the south, possibly because of local winds channeled by topography in the impact basin. This image was intended to match the approximate illumination and viewing conditions of an earlier HiRISE observation that was made 2 Martian years earlier in August 2008. Detailed comparison of the two images shows movements on many of the dunes during this interval of nearly 4 Earth years. Winds from the west have shifted the small ripples up the back of the dune towards the east. Sand has blown over the crest of the dune, cascaded down the steep slip face, and accumulated along the base of the slip face in the lee of the dune. In this way, the small dune advances slowly downwind. Other images also show dune activity in this latitude band, adding to a growing suspicion that dunes are on the move everywhere on Mars, faster in some places than others.
incredible. Amazing.
Gully monitoring on crater slopes in Terra Serenum. These crater gullies lie on the northern wall of an unnamed 9-kilometer diameter southern hemisphere crater in Terra Serenum. The image was acquired during early winter in the southern hemisphere, so the crater wall is in shadow. These gullies were first imaged by HiRISE in 2006. Since that time, the possible role of seasonal frost in gully formation, along with the association of polygonal terrain with these and other gullies, has garnered considerable interest. As a result, these gullies have become one of several locations being monitored by HiRISE throughout multiple Mars years. Over a dozen images of these gullies have been acquired to date throughout different Mars seasons. In this image, frost, likely water ice, is once again forming on these southern hemisphere mid-latitude crater slopes. Close-ups show gullies on the shadowed polar-facing slope. The large dynamic range of the HiRISE camera allows one to see into the shadows dimly lit by sunlight, scattered by the surface and the atmosphere. These gullies are thinly veiled with frost and range in width from several meters to tens of meters, and in length from a couple kilometers or so. Dark regions within the gullies are warmer areas where frost likely evaporated or melted, exposing the darker underlying surface. Colorful dunes. This field of dunes lies on the floor of an old crater in Noachis Terra, one of the oldest places on Mars. When there are perfect conditions for producing sand dunes, steady wind in one direction, and just enough sand, Barkhan sand dunes form. The word Barkhan is a Russian term because this type of dune was first described in the desert regions of Turkestan. Barkhans have a gentle slope on the upwind side and a much steeper slope on the lee side, where horns or a notch often forms. The wind in this case came from the southwest. Observing dunes on Mars can tell us how strong the winds are, as well as their direction. If pictures are taken at regular intervals, one may see changes in the dunes and in ripples on the dune surface. The color in the photograph is not the same as we would see with our eyes, because an extra color, infrared, is added. Our eyes cannot detect infrared, but it is used because it can give us clues to the composition of the surface. On Mars, dunes are often dark in color because they were formed from the common volcanic rock basalt. In the dry environment, dark minerals in basalt, like olivine and pyroxene, do not break down as quickly as they do on Earth. Although rare, some dark sand is found on Earth, for example, in Hawaii, which also has many volcanoes discharging basalt. 2 generations of windblown sediments. This colorful scene is situated in the Noctis labyrinthus, perched high on the Tharsis Rise in the upper reaches of the Valles Marineris Canyon system. Targeting the bright-rimmed bedrock knobs, this image also captures the interaction of 2 distinct types of windblown sediments. Surrounding the bedrock knobs is a network of pale reddish ridges with a complex interlinked morphology. These pale ridges resemble the simpler transverse aeolian ridges called tars that are common in the equatorial regions of Mars. The tars are still poorly understood and are variously ascribed to dunes produced by reversing winds, coarse-grained ripples, or indurated dust deposits. HiRISE observations of tars have so far shown these bed forms are stable over time, suggesting either that they form slowly over much longer timescales than the duration of MRO's mission, or that they formed in the past during periods of very different atmospheric conditions than the present. Dark sand dunes comprise the second type of windblown sediment visible in this image. The dark sand dune seen just below the center of the cutout displays features that are common to active sand dunes observed by HiRISE elsewhere on Mars, including sets of small ripples crisscrossing to the top of the dune. In many cases, it is the motion of these smaller ripples that drives the advance of Martian sand dunes. The dark dunes are made up of grains composed of iron-rich minerals derived from volcanic rocks on Mars, unlike the pale quartz-rich dunes typical of Earth. This image clearly shows the dark sand dunes situated on top of the pale tar network, indicating that the sand dunes are younger than the tars. Moreover, the fresh appearance of the sand dunes suggests that they are currently active and may help shape the unusual tar morphology by sandblasting the tars in the present-day environment. Layers, bedrock ridges, and dark sand in Schiaparelli crater. Like any diverse group of explorers, scientists on the HiRISE team and the general public who submit target suggestions have different goals and interests for the Mars images they hope to get. More often than not, an image intended for one particular science investigation ends up having many other applications, answering and raising new questions. This image was targeted to look at potential changes in the distribution of dark sand compared to earlier pictures. In a preliminary investigation, no such changes have been found, although we will keep looking. Originally, this area, a crater within the larger Schiaparelli crater, was targeted to investigate the circumferential layers that fill the crater, evidence for possible past deposition from airfall dust or even water. In this image, we note something that becomes apparent if we zoom into many of the areas containing dark sand. Here, the sand is on top of the periodic bedrock edges, oriented semi-radially from the crater and approximately perpendicular to the layers. How did these ridges form, and what is the relationship to the sand? The ridge origin is a mystery, but the sand may simply be nucleating on the ridges. This suggests that some apparent large ripples on Mars are sand nucleation sites on pre-existing topography. The extent of such ridges and their relationship to sand elsewhere on the planet can be further understood with future HiRISE images in other areas.